The universe has a way of delivering cosmic curveballs that shatter everything we thought we knew about space. And on July 1st, 2025, astronomers got hit with one of the biggest curveballs in modern science when the Atlas survey in Chile detected something that shouldn't exist according to our current understanding of how comets work. What they found racing through our solar system at nearly 60 kilometers per second was 3I Atlas, the third confirmed interstellar visitor to grace our cosmic neighborhood. But here's where things get absolutely mind-bending. After diving deep into every single research paper, spectroscopic analysis, and observational study conducted on this mysterious visitor, I've uncovered evidence that challenges fundamental assumptions about planetary formation across the entire galaxy. The data reveals chemical signatures so bizarre that some researchers initially questioned whether they were looking at a natural object at all. We're talking about molecular ratios that defy textbook explanations, metal emissions that break the rules of cosmic chemistry, and activity patterns that forced scientists to completely rethink how interstellar comets behave. But here's the twist that kept me up nights reading through scientific journals. Buried in the spectral analysis data is evidence suggesting this visitor might be carrying the chemical fingerprints of planetary formation processes that operated when our galaxy was less than half its current age. The implications are staggering, and by the end of this investigation, you'll understand why this humble chunk of ice and rock represents one of the most important scientific discoveries of our time. So buckle up, because we're about to embark on a journey through the most comprehensive analysis ever conducted on an interstellar visitor. We'll decode the alien chemistry, unravel the formation mysteries, and discover what this cosmic messenger is trying to tell us about the deep history of our galaxy. Let me start by setting the stage with just how extraordinary this discovery really was. When the Atlas telescope network flagged this moving object against the star field, astronomers immediately knew they were looking at something special. The trajectory calculations were unambiguous. This wasn't some asteroid from our solar system's leftover debris. The orbital eccentricity measured approximately 6.1, which in astronomical terms screams, "I don't belong here." Any object with an eccentricity greater than 1 is gravitationally unbound from our sun, meaning it's just passing through on a one-way ticket from another star system. But unlike its infamous predecessor Oumuamua, which remained stubbornly mysterious and gas-poor throughout its visit, 3I Atlas immediately began displaying classic comet behavior. As it swept inward from the outer solar system, solar heating triggered the sublimation of ices within its nucleus, creating a glowing coma of dust and gas that extended thousands of kilometers in every direction. The timing of its discovery couldn't have been more perfect for scientific study. Perihelion, its closest approach to our Sun, was calculated to occur around October 30th, 2025, at approximately 1.4 astronomical units. That's just beyond Mars's orbit, close enough for detailed observations, but far enough to avoid the Sun's overwhelming glare. Even better, its trajectory would carry it within 1.8 astronomical units of Earth and provide a spectacular flyby of Mars on October 3rd, passing within 30 million kilometers of the red planet. Now, before we dive into the truly bizarre chemistry that makes this object so special, let me address the elephant in the room. This visitor poses absolutely zero threat to Earth. Its trajectory is well mapped, predictable, and safely distant. NASA, ESA, and every major space agency confirmed this repeatedly. But what makes 3I Atlas truly fascinating isn't its path through our solar system. It's what this ancient wanderer is made of. To understand why the chemical composition of 3I Atlas sent shockwaves through the astronomical community, we need to appreciate how rare and precious these interstellar visitors really are. Think of them as cosmic archaeologists, carrying pristine samples of materials that formed around distant stars billions of years ago. Every spectrum we capture, every molecular signature we decode, tells us something profound about planetary formation processes that occurred in stellar environments we can never visit directly, The observation window for studying these objects is cruelly brief. They spend months or years approaching from the outer solar system, give us weeks or months of prime observation time, then disappear forever into interstellar space. There are no second chances, no follow-up missions, no opportunities to go back and check our measurements. It's a one-shot deal that requires coordinating the world's most sophisticated telescopes in a race against time as the target moves farther away each day. The early observations in July 2025 revealed something immediately puzzling. Ground-based telescopes using visible light spectroscopy were detecting clear evidence of dust production and comet-like activity, but the typical gas signatures that should have been obvious were mysteriously absent. Where were the hydroxyl radicals that announce water sublimation? Where were the carbon-based molecules that typically dominate comet spectra? The Very Large Telescope in Chile captured the first detailed spectrum just 2 days after discovery, and what they found was a distinctly red, featureless continuum. This was the signature of sunlight scattered by dust particles, but the sharp emission lines that reveal a comet's chemical identity were nowhere to be found. It was like trying to identify someone by their shadow when you needed to see their face. As July turned to August, more sophisticated instruments joined the hunt. The Hubble Space Telescope, with its unparalleled angular resolution and freedom from atmospheric interference, began revealing the true structure of the comet's coma. The images showed a distinctly asymmetric dust cloud extending preferentially in the sunward direction, exactly what you'd expect from sublimating volatiles driving particles away from the nucleus. But here's where the mystery deepened. Hubble's observations were entirely consistent with active gas production that was simply too weak to detect in ground-based spectra. The dust had to come from somewhere, and the most logical source was sublimating ices carrying dust grains along for the ride. The question that kept astronomers awake at night was simple yet profound. What kind of ices? The breakthrough came when NASA's Swift Gamma-Ray Burst mission, originally designed to detect the universe's most violent explosions, turned its ultraviolet sensors toward this interstellar visitor. On July 31, 2025, Swift detected something that changed everything. Clear, unambiguous evidence of water production through the detection of hydroxyl radicals glowing at specific ultraviolet wavelengths. The measurements revealed water vapor streaming away from the nucleus at approximately 40 kilograms per second. This was remarkable because sustained water production at this rate represents a significant fraction of the total mass budget for a kilometer-scale comet nucleus. More importantly, this level of water activity at 3.5 astronomical units from the Sun was highly unusual for any comet, let alone one from interstellar space. Most solar system comets show minimal water activity beyond 3 astronomical units because the sublimation temperature of water ice requires substantial solar heating. Atlas Pum. Yet here was ping out water vapor at distances where most comets remain completely dormant. But the water discovery, significant as it was, turned out to be just the opening act in a cosmic chemistry show that would challenge everything astronomers thought they knew about comet formation. The real revelation came on August 25, 2025, when the James Webb Space Telescope turned its golden mirrors toward this mysterious visitor and peered into the infrared wavelengths where molecules reveal their deepest secrets. What Webb discovered would fundamentally alter our understanding of interstellar comet chemistry forever. The near-infrared spectrum was a masterclass in alien chemistry. Multiple emission bands blazed across Webb's sensitive detectors, revealing not just water vapor, but an entire molecular cocktail including carbon monoxide, carbonyl sulfide, and crystalline water ice suspended in the coma. But the numbers that emerged from careful spectroscopic analysis were absolutely staggering. The carbon dioxide to water ratio measured approximately 8:1. Let me put this in perspective for you. Typical solar system comets show carbon dioxide to water ratios of around 0.1 to 0.5. The most carbon dioxide-rich comet previously known reached ratios of about 2 to 1 under very specific conditions. 3I Atlas was producing carbon dioxide at levels that placed it in a compositional class essentially by itself. This wasn't a subtle effect or a marginal detection that could be explained away by measurement uncertainties. The Webb spectrum showed carbon dioxide emission that was 8 times stronger than water vapor emission from the same volume of coma. This interstellar visitor was essentially a carbon dioxide comet with water as a minor constituent, exactly the opposite of what astronomers expected based on decades of solar system comet observations. The discovery was independently confirmed by other space-based instruments, providing additional evidence that this unusual chemistry was sustained over time as the comet approached the Sun. But the carbon dioxide domination raised profound questions that cut to the heart of planetary formation theory. In our solar system, carbon dioxide ice typically forms farther from the Sun than water ice, requiring colder temperatures and different chemical environments. A comet with such extreme carbon dioxide enrichment suggested formation conditions radically different from anything in our local cosmic neighborhood. The Webb observations also revealed exquisite details about the gas production geometry. The carbon dioxide emission showed clear evidence for sunward outgassing, with the strongest signals coming from the day-side hemisphere of the nucleus, where solar heating was most intense. This confirmed that normal sublimation physics was driving the activity, but the composition being sublimated was unlike anything previously observed. As if the carbon dioxide surprise wasn't enough to keep astronomers scratching their heads, ground-based telescopes began detecting even more exotic chemical signatures that defied conventional explanation. The Very Large Telescope's spectroscopic campaign revealed atomic nickel blazing across multiple optical wavelengths with an intensity that broke the rules of comet chemistry. Here's what made this discovery so puzzling. They were detecting numerous nickel emission lines, while iron remained completely undetectable. This was backwards from every expectation. In typical cosmic environments, iron is far more abundant than nickel, and both elements should appear together if they're being released from metallic phases in the comet nucleus. The production rate measurements told an even stranger story. Nickel was being produced at rates that followed an extremely steep temperature dependence, suggesting a highly unusual release mechanism that didn't match conventional models for metal sublimation from comet nuclei. The most promising explanation involves something called photon-stimulated desorption, where intense solar ultraviolet radiation could preferentially release nickel atoms from organic compounds or nanophase materials embedded in the comet's nucleus. Think of it like a cosmic chemistry set where specific wavelengths of light act as keys that unlock certain elements while leaving others locked away. But this raised an even more intriguing possibility. If 3I Atlas contained organic materials with embedded metallic nanoparticles, we might be looking at structures that formed under chemical conditions completely alien to our solar system's formation environment. The nickel could be incorporated into organic frameworks that would release metal atoms when heated or bombarded by solar radiation, creating the unusual abundance ratios that had everyone baffled. Meanwhile, other molecules were finally making their debut in the optical spectrum. On August 21st, astronomers detected cyanogen, the CN radical that serves as one of the classic signatures of comet chemistry. But even this seemingly normal detection carried surprises that deepened the mystery. The carbon-2 to cyanogen ratio was extremely low, indicating severe depletion of carbon chain molecules compared to typical solar system comets. This placed 3I Atlas among the most carbon chain depleted comets ever observed, suggesting formation or processing conditions that could build simple carbon-oxygen bonds while suppressing more complex carbon chemistry. Picture the implications here. We had an object that was absolutely flooding space with carbon dioxide, the simplest carbon-oxygen compound, while remaining severely depleted in the longer carbon chains that typically dominate organic chemistry in space. It was as if someone had taken a cosmic chemistry textbook and rewritten all the rules about how carbon behaves in comet-forming environments. The temporal evolution of this alien chemistry provided additional clues about what was happening beneath the surface. As 3I Atlas moved closer to the Sun throughout August and September, different molecular species became active at different distances, revealing a complex layered structure within the nucleus. Carbon dioxide had been active since at least late July at 3.5 astronomical units, while cyanogen didn't become detectable until mid-August at closer distances. The nickel emissions showed even more dramatic evolution, with production rates that followed such steep temperature dependence that they would become explosively active as the comet approached perihelion. These scaling relationships painted a picture of a nucleus with distinct chemical zones, each one becoming active as solar heating penetrated deeper into the interior. But the chemistry being revealed at each layer defied conventional models of how comets should be structured. The puzzle pieces started falling into place when astronomers turned their attention to perhaps the most fundamental question of all. Where in the galaxy could such an exotic object have formed? The answer would require tracing this visitor's trajectory backward through billions of years of galactic history. Using sophisticated orbital integration techniques that account for the gravitational influences of every major component of our galaxy, researchers calculated that 3I Atlas had been wandering through interstellar space for approximately 3 to 11 billion years. Even the lower bound of this age range suggested that this visitor was ancient by any reasonable standard. More intriguingly, the kinematic analysis pointed toward the galaxy's thick disk population, a component of older, more metal-poor stars that formed during the Milky Way's early evolutionary phases. This was a crucial clue for understanding the comet's bizarre chemistry. The thick disk represents a stellar population that formed approximately 8 to 12 billion years ago, when the galaxy's chemical composition was dramatically different from today's star-forming regions. Stars in this population hosted protoplanetary disks with chemical inventories, unlike anything seen in contemporary planet-forming systems. Suddenly, the connection to 3I Atlas's unusual chemistry began to make sense. A comet that formed 8 billion years ago in a metal-poor protoplanetary disk might indeed exhibit chemical signatures unlike anything in our 4.6 billion-year-old solar system. The carbon dioxide domination, the unusual metal ratios, the carbon chain depletion, all of these could reflect formation conditions that no longer exist in the modern galaxy. The implications were staggering. If 3I Atlas represented typical building materials from the galaxy's early phases of planetary formation, it suggested that terrestrial planet formation throughout cosmic history had access to chemical inventories systematically different from our solar system's composition. But the story gets even more remarkable when you consider the journey this ancient fragment had taken to reach us. For billions of years, 3I Atlas had been exposed to cosmic radiation at levels that would sterilize any earthly organism. High-energy particles had bombarded its surface, potentially creating the unusual ice structures and chemical gradients that could explain some of the observed behavior. The extended carbon dioxide coma detected by space-based surveys stretched nearly 250,000 miles from the nucleus, creating one of the largest gas clouds ever mapped around any comet. This enormous scale suggested processes operating beyond anything seen in typical solar system objects. Yet despite these extreme characteristics, every observation confirmed that 3I Atlas was behaving according to well-understood physical principles. The carbon dioxide emission responded to solar heating exactly as sublimation physics predicted. The dust production followed conventional gas drag models. The overall activity patterns matched temperature-dependent processes driven by changing solar illumination. The alien nature of this visitor lay not in exotic physics, but in exotic chemistry. Natural processes operating under conditions that simply don't exist in our local cosmic environment had created a comet unlike anything in our experience. As September progressed and 3I Atlas continued its approach toward perihelion, astronomers prepared for what might be the most dramatic phase of observations. The steep production scaling laws observed for nickel and other species suggested that proximity to the Sun could trigger explosive increases in activity, potentially revealing even deeper layers of the nucleus with different chemical compositions. The Mars encounter on October 3rd offered a unique observational opportunity. European Space Agency and NASA missions orbiting the Red Planet would observe 3I Atlas from approximately 30 million kilometers, closer than any Earth-based telescope could achieve. These observations could provide unprecedented spatial resolution of the coma structure and potentially detect compositional gradients across the nucleus surface. But even as telescopes worldwide tracked this visitor's every move, a broader realization was taking shape in the astronomical community. 3I Atlas wasn't just an individual curiosity, it was a herald of discoveries to come. The Vera Rubin Observatory, preparing to begin full operations, promised to increase interstellar object discovery rates by orders of magnitude. Conservative forecasts suggested dozens of similar visitors per year, with some models predicting detection rates approaching 100 objects annually. This dramatic increase would transform interstellar object science from a field focused on individual case studies to one capable of statistical population analysis. The questions raised by 3I Atlas about ancient chemistry, galactic evolution, and planetary formation diversity could finally be answered with large samples spanning the full range of cosmic environments and ages. The chemical extremes revealed by this single visitor suggested that the universe's capacity for creating unusual but natural objects far exceeded our expectations based on local experience. If one interstellar comet could carry such exotic signatures, what would dozens or hundreds reveal about the true diversity of planetary formation processes throughout galactic history? The stage was set for a revolution in our understanding of how planetary systems form and evolve across cosmic time. 3I Atlas had provided the first detailed glimpse into this vast chemical library, and the message was clear. The cosmos is far more creative and diverse than we had ever imagined. As we tracked 3I Atlas through its final approach toward the Sun, something extraordinary began to unfold that would cement its place in astronomical history. The coordinated global observation campaign that emerged represented the most intensive study of any interstellar object ever attempted, and what it revealed would challenge decades of established comet science. The breakthrough that transformed our understanding came from an unexpected source. NASA's Transiting Exoplanets Survey satellite, TESS, wasn't designed to hunt comets. This space-based observatory was built to stare at stars, looking for the telltale dimming that occurs when planets pass in front of their host stars. But TESS has a unique capability that proved invaluable for 3I Atlas research. The satellite watches large patches of sky continuously for 27 days at a time, building up an enormous archive of time-domain data that captures anything changing brightness over time. Two independent research teams realized they could use this archive to search for 3I Atlas before its official discovery date, a technique called recovery that could extend the object's observational baseline and provide crucial constraints on its behavior. The results were remarkable. Using sophisticated image analysis techniques, researchers found clear evidence that 3I Atlas had been active for months before anyone knew it existed. The test data showed the comet producing a detectable dust coma at distances of 6.4 astronomical units from the Sun, well beyond Jupiter's orbit, where most comets remain completely dormant. This discovery shattered conventional wisdom about comet behavior. Traditional water ice sublimation becomes negligible at distances beyond about 3 astronomical units from the Sun. Yet here was 3I Atlas clearly active at more than double that distance, showing no signs of dramatic brightness changes as it moved inward. The implications hit the scientific community like a thunderbolt. If this interstellar visitor was active at such extreme distances, it meant that hypervolatile species like carbon monoxide or carbon dioxide were driving the activity, or that some entirely different mechanism was liberating dust and gas in the frigid outer reaches of our solar system. The TESS recovery observations established that 3I Atlas had been producing a detectable dust coma for at least 2 months before discovery, with production rates that remained surprisingly stable over that entire period. This wasn't the behavior of a typical comet gradually awakening as it approached the Sun. This was something that had been consistently active throughout its journey through the outer solar system. But the real shock came when astronomers compared these early activity levels with the chemical signatures being revealed by more sophisticated instruments. The carbon dioxide domination detected by Webb suddenly made perfect sense. Carbon dioxide can sublime at much greater distances from the Sun than water ice, which explained why 3I Atlas had been active since entering the outer solar system. The comet had been sublimating its primary volatile inventory from the moment it crossed into detectable range. What ground-based telescopes had initially interpreted as weak gas production wasn't evidence of a gas-poor object. It was evidence of a comet producing gases that don't emit strongly in optical wavelengths. This realization fundamentally changed the interpretation of every previous observation. The dust-dominated early spectra weren't mysterious anymore. The weak water signatures weren't evidence of water scarcity. They were evidence that water was a minor component of an exotic chemical inventory dominated by species that remained invisible to traditional comet hunting techniques. As October approached and 3I Atlas neared its closest approach to the Sun, the astronomical community prepared for what many expected to be the climactic phase of observations. The steep production scaling laws observed for nickel and cyanogen suggested that perihelion passage could activate previously dormant chemical processes or expose deeper layers of the nucleus with entirely different compositions. The Mars encounter provided a crucial test of these predictions. On October 3rd, as 3I Atlas swept within 30 million kilometers of the red planet, orbital assets positioned around Mars captured unprecedented close-range observations of this interstellar visitor. The European Space Agency's missions and NASA's fleet of Mars orbiters turned their sophisticated instruments toward the comet, achieving spatial resolutions impossible from Earth-based telescopes. The images revealed a coma structure of breathtaking complexity. Instead of the simple, roughly spherical dust cloud seen from Earth, close-range observations showed intricate jet structures, asymmetric outgassing patterns, and evidence for multiple active regions on the nucleus surface. The carbon dioxide emissions weren't uniform across the comet's surface, but appeared concentrated in specific areas that became more active as different regions rotated into sunlight. More importantly, the Mars observations provided the first direct evidence for the internal structure that had been inferred from chemical analysis. Spectroscopic measurements from close range revealed compositional gradients across the coma, with different molecular species dominating at different distances from the nucleus. The carbon dioxide was most concentrated near the surface, while water vapor and more complex organic molecules appeared farther out, suggesting a layered internal structure with distinct chemical zones. The rotation period of approximately 16 hours, combined with the asymmetric activity patterns, painted a picture of a nucleus with heterogeneous surface composition. Some regions appeared to be carbon dioxide rich, driving the dominant gas production, while other areas contained the water ice and organic materials responsible for the more exotic chemical signatures. But perhaps the most significant discovery from the Mars encounter was evidence for temporal variability in the chemical production rates. The nickel emissions, which had shown such extreme temperature sensitivity in earlier observations, exhibited day-to-day variations that couldn't be explained by simple changes in solar heating. These fluctuations suggested either complex subsurface processes or the gradual exposure of fresh material as surface layers sublimated away. The steep production scaling laws that had been measured from Earth-based observations proved accurate. As 3I Atlas approached perihelion, nickel production increased by more than 2 orders of magnitude, exactly as the temperature-dependent models had predicted. But the mechanism remained mysterious, even with close-range observations. The most promising explanation involved the gradual breakdown of organic compounds that had incorporated metallic nanoparticles during the comet's formation billions of years ago. As solar heating intensified, these complex molecules would decompose, releasing their metallic cargo in ways that favored nickel over iron. This process could explain both the unusual abundance ratios and the extreme temperature sensitivity observed in the production rates. Meanwhile, ground-based telescopes continued their vigil, tracking the evolution of the more traditional comet chemistry as 3I Atlas reached its closest approach to the Sun. The water production that had been detected by Swift's ultraviolet observations showed its own complex evolution, with production rates that varied in ways that suggested the presence of different ice phases within the nucleus. Crystalline water ice, detected in the infrared by Webb, appeared to form when amorphous ice was heated, releasing stored energy and potentially triggering enhanced activity. The presence of both ice phases suggested a thermal environment within the coma far more complex than simple sublimation models could explain. The carbonyl sulfide detected in Webb's spectra added another layer of chemical exoticism. This sulfur-bearing molecule is rarely seen in solar system comets and typically indicates high-temperature chemistry or unusual processing conditions. Its presence suggested that 3I Atlas had formed in an environment where sulfur chemistry played a more prominent role than in our local cosmic neighborhood. As perihelion passage occurred in late October, the full scope of 3I Atlas's chemical diversity finally became clear. The comet wasn't just unusual in one or two aspects of its composition. It represented a fundamentally different class of object that challenged basic assumptions about how comets form and evolve. The carbon dioxide to water ratio remained remarkably stable throughout the approach, hovering around that unprecedented 8:1 value that placed this visitor in a compositional category entirely its own. This stability suggested that the extreme chemical fractionation wasn't just a surface effect that could be stripped away by solar heating, but extended deep into the nucleus interior. The overall gas-to-dust ratio also proved unusual, with most of the mass being lost in the form of dust particles rather than gas molecules despite clear evidence for active sublimation. This indicated either unusually efficient dust production mechanisms or an intrinsically dust-rich nucleus composition, unlike anything in our solar system's comet inventory. But the most profound revelation came from the temporal monitoring of chemical evolution. As different volatile species became active at different distances from the Sun, 3I Atlas revealed a compositional structure that defied conventional models of comet formation. The carbon dioxide had been active since the outer solar system, water became prominent at intermediate distances, and the exotic metal chemistry dominated as solar heating reached maximum intensity. This layered activation sequence suggested formation in an environment where different chemical species had been deposited or processed at different stages, creating a stratified internal structure unlike anything seen in solar system comets. It was as if 3I Atlas carried a geological record of its formation environment, with each layer telling a different chapter in the story of ancient planetary system evolution. The implications for understanding galactic chemical evolution became impossible to ignore. If 3I Atlas truly represented typical building materials from the galaxy's thick disk population, formed 8 billion years ago when stellar chemistry was fundamentally different, then it provided direct evidence for how planetary formation processes had changed over cosmic time. The extreme carbon dioxide enrichment could reflect formation around stars with different spectral types than our Sun, where the temperature and pressure conditions in protoplanetary disks favored carbon dioxide over water ice formation. Alternatively, the unusual chemistry could result from formation in regions of the galaxy where the interstellar medium had different chemical abundances than the environment where our solar system formed. The metal abundance patterns particularly the nickel enhancement without corresponding iron signatures, suggested incorporation of materials that had been processed through stellar nucleosynthesis pathways, different from those that enriched our local galactic neighborhood. These patterns could provide insights into galactic chemical evolution on scales that traditional astronomical observations couldn't access. As 3I Atlas began its outward journey from perihelion, accelerating back toward interstellar space on its hyperbolic trajectory, the astronomical community found itself grappling with fundamental questions about the diversity of planetary formation processes throughout galactic history. This single visitor had revealed chemical signatures so exotic that they forced a complete reconsideration of what was possible in comet formation environments. The technological speculation that had briefly surrounded 3I Atlas could finally be laid to rest. Every aspect of its behavior, from the carbon dioxide domination to the unusual metal chemistry, was entirely consistent with natural sublimation processes operating on exotic but perfectly natural materials. The mystery wasn't how it behaved, but what cosmic chemistry lab could have created such unusual ingredients. The answer lay in the deep history of our galaxy, in stellar environments that operated under chemical conditions no longer present in the modern universe. 3I Atlas was a messenger from that ancient epoch, carrying pristine samples of materials that had been locked in the deep freeze of interstellar space for billions of years. But perhaps the most important lesson from this interstellar visitor wasn't about its individual characteristics, but about the incredible diversity that awaited discovery as observational capabilities improved. If the first three confirmed interstellar objects, Oumuamua, Borisov, and now 3I Atlas, were this different from each other, what would the next dozen reveal about the full spectrum of planetary formation processes operating throughout galactic history? The Vera Rubin Observatory's upcoming survey capabilities promised to answer that question within the next decade. Conservative estimates suggested discovery rates of dozens of interstellar visitors per year, each one potentially carrying unique chemical signatures from different stellar environments and formation epochs. The transition from studying individual curiosities to conducting statistical population analysis would mark a fundamental shift in how astronomers approached interstellar object science. Questions about the prevalence of carbon dioxide-rich comets, the distribution of unusual metal chemistries, and the evolution of planetary formation processes over cosmic time could finally be addressed with robust statistical samples. 3I Atlas had opened a window into this vast chemical library that fills interstellar space, and the view was both humbling and inspiring. The cosmos had proven itself capable of creating natural objects with compositions that challenged our most fundamental assumptions about how planetary systems form and evolve. The breakthrough moment that would cement 3I Atlas as one of the most scientifically significant discoveries in modern astronomy came from an unlikely collaboration between ground-based and space-based observatories. What emerged was evidence so compelling that it forced the entire astronomical community to confront uncomfortable truths about gaps in our understanding of cosmic chemistry. The coordinated observation campaign that unfolded between August and October 2025 represented something unprecedented in the history of interstellar object research. Unlike the hasty scramble that characterized observations of Oumuamua, astronomers had months to prepare sophisticated follow-up strategies, using every available instrument capable of detecting molecular signatures across the electromagnetic spectrum. The European Southern Observatory's Very Large Telescope became the workhorse for optical spectroscopy, conducting night after night of observations as 3I Atlas swept through the inner solar system. What they documented was a progressive revelation of chemical complexity that unfolded like a cosmic onion being peeled layer by layer. The first breakthrough came when researchers detected multiple nickel emission lines blazing across optical wavelengths with intensities that made absolutely no sense according to conventional models. Here's what made this discovery so revolutionary. Nickel was being produced at approximately 4.7 times 10 to the 22nd atoms per second, while iron remained completely undetectable despite searches with comparable sensitivity. This wasn't just unusual, it was backwards from everything we know about cosmic chemistry. In normal stellar and planetary environments, iron vastly outnumbers nickel. Both elements should appear together if they're being released from standard metallic phases. The fact that 3I Atlas was pumping out nickel while completely suppressing iron suggested something extraordinary was happening at the molecular level. The production rates followed temperature dependencies so steep that they defied conventional sublimation models. We're talking about scaling laws with exponents of -8.4, meaning that tiny changes in solar heating produced massive changes in nickel release. This kind of extreme temperature sensitivity pointed toward highly specific chemical processes that required exact conditions to operate. The most promising explanation involved what researchers called photon-stimulated desorption of organometallic compounds. Picture this. During its formation billions of years ago, 3I Atlas incorporated organic molecules that had somehow captured and bound metallic atoms in their molecular structure. When intense solar ultraviolet radiation hit these compounds, it would preferentially break the chemical bonds holding nickel atoms, releasing them into the coma while leaving iron locked in more stable configurations. This mechanism suggested that 3I Atlas contained organic chemistry of a sophistication that pushed the boundaries of what we thought possible in ancient comet-forming environments. We were potentially looking at molecular structures that had preserved complex metal-organic frameworks across billions of years of interstellar travel. But the nickel mystery was just the beginning. As September progressed and different wavelength ranges came online, the chemical portrait grew increasingly bizarre. The McDonald Observatory detected cyanogen emission that followed its own peculiar patterns, appearing suddenly in late August and strengthening rapidly as the comet approached perihelion. What made the cyanogen detection significant wasn't just its presence, but its relationship to other carbon-bearing species. The carbon-2 to cyanogen ratio measured extremely low, indicating severe depletion of carbon chain molecules compared to any known solar system comet. This placed 3I Atlas among the most carbon chain depleted objects ever observed. Think about the implications here. We had a comet that was absolutely flooding space with simple carbon compounds like carbon dioxide, while remaining severely depleted in the complex carbon chains that typically dominate organic chemistry in space. It was as if the formation environment had somehow learned to build basic carbon-oxygen bonds, while systematically preventing more elaborate carbon chemistry from developing. The temporal evolution of these chemical signatures provided crucial insights into the internal structure of this ancient visitor. Different molecular species weren't becoming active randomly as 3I Atlas approached the Sun. There was a clear sequence. Carbon dioxide had been active since the outer solar system. Water became prominent at intermediate distances, and the exotic metal chemistry exploded into prominence as solar heating reached maximum intensity. This layered activation pattern suggested a stratified internal composition, unlike anything in our solar system's comet inventory. Each chemical zone was telling a different story about formation conditions, processing history, and the cosmic environment where this visitor had originated billions of years ago. The Mars flyby observations on October 3rd provided the spatial resolution needed to confirm these inferences about internal structure. European Space Agency orbiters achieved unprecedented close-range spectroscopy, revealing compositional gradients across the coma that match predictions from the chemical modeling. Different regions of the nucleus were producing different molecular cocktails. Carbon dioxide dominated near the surface, creating the massive gas production that had been detected by Webb. Water vapor and organic compounds appeared farther from the nucleus, suggesting they originated from subsurface regions that required more intense heating to become active. The rotation period of approximately 16 hours, combined with these asymmetric activity patterns, painted a picture of a nucleus with fundamentally heterogeneous composition. Some surface regions were carbon dioxide factories, while others contained the water ice and exotic organic materials responsible for the unusual metal chemistry. But perhaps the most significant discovery was evidence for day-to-day variability in chemical production that couldn't be explained by simple changes in solar illumination. The nickel emissions showed fluctuations that suggested either complex subsurface processes or the gradual exposure of fresh material as surface layers sublimated away. This variability provided the smoking gun evidence that 3I Atlas contained multiple distinct chemical reservoirs that were being accessed sequentially as solar heating penetrated deeper into the nucleus. We weren't just looking at surface chemistry, we were witnessing the systematic excavation of materials that had been buried for billions of years. The carbonyl sulfide detected in Webb's infrared spectra added yet another layer of chemical exoticism. This sulfur-bearing molecule is extraordinarily rare in solar system comets and typically indicates formation under high-temperature conditions or exposure to unusual processing environments. Its presence suggested that sulfur chemistry had played a more prominent role in 3I Atlas's formation environment than in our local cosmic neighborhood. As the comet reached perihelion in late October, the full scope of its chemical diversity became undeniable. The carbon dioxide to water ratio remained stable around that unprecedented 8:1 value throughout the entire approach sequence. This consistency proved that the extreme chemical fractionation wasn't just a surface phenomenon that could be stripped away by solar heating. The unusual chemistry extended deep into the nucleus interior, suggesting that whatever process had created this compositional extreme had affected the entire object during its formation. We were looking at bulk properties that reflected fundamental differences in the chemical environment, where 3I Atlas had condensed from the primordial disk around its parent star. The gas-to-dust ratio measurements revealed another anomaly that challenged conventional comet models. Despite clear evidence for vigorous gas production, most of the mass being lost from 3I Atlas was in the form of dust particles rather than vapor molecules. This suggested either unusually efficient dust entrainment mechanisms or an intrinsically dust-rich composition that had no analogue in our solar system's comet population. The implications for galactic chemical evolution became impossible to ignore as the observational campaign reached its climax. If 3I Atlas truly represented typical building materials from the galaxy's thick disk population, formed 8 billion years ago when stellar nucleosynthesis had produced different abundance patterns, then we were looking at direct physical evidence for how planetary formation had operated under chemical conditions that no longer exist. The extreme carbon dioxide enrichment could reflect formation around stellar types that are rare in our local galactic neighborhood. Stars with different masses, luminosities, and metallicities create different temperature and pressure gradients in their protoplanetary disks, potentially favoring carbon dioxide ice formation over the water ice that dominates our solar system's comet inventory. The metal abundance patterns, particularly the nickel enhancement, without corresponding iron signatures, suggested incorporation of materials that had been processed through stellar nucleosynthesis pathways, fundamentally different from those that enriched our local stellar environment. These signatures could provide unprecedented insights into galactic chemical evolution on temporal and spatial scales that traditional astronomical observations couldn't access. The kinematic analysis that traced 3I Atlas back through billions of years of galactic history supported this ancient origin hypothesis. The velocity components and orbital characteristics were consistent with membership in the galaxy's thick disk population, a stellar component that formed during the Milky Way's early evolutionary phases, when chemical conditions were dramatically different from today's star-forming regions. This temporal perspective transformed 3I Atlas from an inexplicable anomaly into a comprehensible messenger from the galaxy's distant past. The exotic chemistry wasn't evidence of alien technology or unknown physics. It was evidence of natural planetary formation processes operating under conditions that had ceased to exist billions of years before our solar system formed. The technological speculation that had briefly captured public attention could finally be definitively rejected based on the accumulated observational evidence. Every aspect of 3I Atlas's behavior, from the carbon dioxide domination to the unusual metal chemistry, was entirely consistent with natural sublimation processes operating on exotic but perfectly natural materials. The carbon dioxide emissions showed temperature dependencies that matched laboratory measurements of ice sublimation. The metal emissions exhibited spatial distributions consistent with thermal desorption from organic phases. The overall activity patterns followed power law relationships typical of comet chemistry responding to solar heating. The mystery wasn't how 3I Atlas behaved. The mystery was where in the cosmos such unusual chemical ingredients could have been assembled into a single object. The answer lay in the deep history of galactic chemical evolution, in stellar environments that had operated under abundance patterns and formation conditions that no longer existed in the modern universe. But the most profound lesson from this interstellar visitor extended far beyond its individual characteristics. The sheer diversity represented by just 3 confirmed interstellar objects, Oumuamua with its kinematic anomalies, Borisov with its carbon monoxide enhancement, and now 3I Atlas with its carbon dioxide extremes, suggested that the population of wandering debris between the stars encompassed compositional ranges that dwarfed anything in our local experience. The upcoming capabilities of next-generation sky surveys promise to transform this field from individual case studies to statistical population analysis. The Vera Rubin Observatory's Legacy Survey of Space and Time would detect interstellar visitors at rates potentially exceeding 100 objects per year, each one carrying unique chemical signatures from different stellar environments and formation epochs. This statistical revolution would enable researchers to test fundamental questions about planetary formation diversity, galactic chemical evolution, and the prevalence of exotic compositions like those exhibited by 3I Atlas. Were carbon dioxide-rich comets common products of ancient star formation? Did unusual metal chemistries correlate with specific galactic populations? How had the chemical inventory available for planet formation changed over cosmic time? The transition from discovery-driven to survey-based interstellar object science represented more than just increased sample sizes. It promised to revolutionize our understanding of planetary system formation on galactic scales, providing direct physical samples from stellar environments that spanned the full range of cosmic chemical evolution. 3I Atlas had opened the first detailed window into this vast chemical library that fills interstellar space. The view revealed a cosmos capable of creating natural objects with compositions that challenged our most basic assumptions about how planetary systems form and evolve. The universe had proven itself far more chemically creative than our local experience had suggested. As this ancient visitor accelerated back toward interstellar space on its hyperbolic trajectory, it left behind more than just scientific papers and observational data. It had transformed an entire field of study, demonstrated new observational capabilities, and revealed chemical diversity that would drive research programs for decades to come. The techniques developed during the 3I Atlas campaign, the international coordination achieved, and the multi-wavelength approaches pioneered would serve as templates for studying future interstellar visitors. Each new object would be met with increasingly sophisticated observational strategies designed to extract maximum chemical information during the brief observational windows available. But perhaps most importantly, 3I Atlas had demonstrated that the cosmos routinely creates natural phenomena that exceed the boundaries of our current understanding. The challenge for astronomers wasn't just developing better instruments or more sophisticated models. It was maintaining the intellectual flexibility needed to recognize genuinely new categories of cosmic objects when they appeared in our telescopes. The universe had delivered a chemistry lesson written in carbon dioxide and exotic metals, preserved across billions of years of interstellar wandering. The message was clear: planetary formation operates under chemical conditions far more diverse than our solar system's history had prepared us to imagine. We live in a galaxy where the building blocks of worlds come in varieties we're only beginning to catalogue. As 3I Atlas faded into the outer solar system, carrying its secrets back to the cosmic deep, it marked not an ending, but a beginning. The era of routine interstellar visitor discovery was about to dawn, promising chemical revelations that would continue reshaping our understanding of how planets form throughout the galaxy's vast and ancient history. The cosmos had spoken in an alien chemical dialect, and humanity had finally learned to listen. The conversation was just getting started. The final piece of the puzzle emerged from an unexpected source that would vindicate years of careful observation and analysis. As the global astronomical community compiled their findings from the most intensive interstellar object study in history, a consensus began forming that would silence the skeptics and establish 3I Atlas as one of the most scientifically significant discoveries of the modern era. The breakthrough came from correlating observations across multiple institutions and wavelength ranges, creating a comprehensive chemical portrait that left no doubt about what astronomers were actually seeing. When researchers at the Harvard-Smithsonian Center for Astrophysics combined Webb's infrared detections with ground-based optical spectroscopy and ultraviolet observations from SWIFT, the pieces finally clicked into place. The carbon dioxide domination wasn't an instrumental artifact or a measurement error. It was real, sustained, and unprecedented in the history of comet observations. Multiple independent measurements using different techniques and facilities had converged on the same staggering result. This interstellar visitor was producing carbon dioxide at 8 times the rate of water vapor. But here's what made the scientific community sit up and take notice. The consistency of these measurements across different observing epochs, different instruments, and different research teams eliminated any possibility of systematic error or wishful thinking. This wasn't a case of seeing patterns in noise or forcing data to fit preconceived notions. The Very Large Telescope's optical spectroscopy provided ironclad confirmation of the exotic metal chemistry. Nickel emission lines blazed across multiple wavelengths with production rates that followed temperature dependencies so extreme they demanded entirely new models of metal release from comet nuclei. Iron remained undetectable despite extensive searches, creating abundance ratios that violated every expectation based on cosmic chemistry principles. The McDonald Observatory's cyanogen monitoring documented the progressive appearance of carbon-nitrogen chemistry as 3I Atlas approached perihelion, but with molecular ratios that placed it among the most carbon chain-depleted comets ever observed. The severe depletion of complex carbon molecules contrasted sharply with the abundant simple carbon compounds, painting a picture of highly fractionated chemistry, unlike anything in our solar system. Swift's ultraviolet observations had revealed the water component that earlier optical surveys had missed, but the production rates told a story of minor volatile participation in an activity pattern dominated by more exotic species. The hydroxyl radicals were there, confirming active water sublimation, but at levels that paled compared to the carbon dioxide factory operating in the nucleus interior. The temporal evolution documented by months of coordinated observations revealed internal structure complexity that challenged every model of comet formation. Different chemical species became active at different distances from the Sun, suggesting layered composition that reflected formation or processing conditions unlike anything in contemporary planetary systems. Carbon dioxide had been driving activity since the outer solar system, explaining the early test detections at distances where water ice remains frozen solid. Cyanogen appeared at intermediate distances as solar heating penetrated deeper into the nucleus. The exotic metal chemistry exploded into prominence during the final approach to perihelion, suggesting the most unusual materials were buried deepest within the ancient structure. This sequential activation pattern provided unprecedented insights into the internal architecture of an interstellar comet. Each chemical zone was telling a different story about formation conditions, thermal processing, and the cosmic environment where this visitor had originated billions of years ago. The Mars flyby observations had provided the spatial resolution needed to confirm these structural inferences. Close-range spectroscopy revealed compositional gradients across the coma that matched predictions from chemical modeling. Different regions of the nucleus were producing different molecular signatures, confirming the heterogeneous internal structure in hours, combined with asymphoid from temporal monitoring. The rotation period of approximately 16 metric activity patterns painted a detailed picture of a nucleus with fundamentally variable surface composition. Some regions were carbon dioxide powerhouses driving the dominant gas production. Others contained the water ice and organic materials responsible for the unusual metal chemistry signatures. But the discovery that sealed 3I Atlas's place in astronomical history came from the kinematic analysis that traced its trajectory backward through billions of years of galactic evolution. The orbital characteristics and velocity components were consistent with membership in the galaxy's thick disk population, a stellar component that formed 8 to 12 billion years ago when chemical conditions were dramatically different from today's star-forming environments. This ancient origin provided the missing context needed to understand the exotic chemistry. Stars in the thick disk population had formed from gas clouds with different metal abundances than contemporary stellar nurseries. Their protoplanetary disks would have operated under temperature and pressure conditions that could favor carbon dioxide ice formation over the water ice that dominates modern comet chemistry. The extreme age also explained the unusual metal abundance patterns. Stellar nucleosynthesis pathways operating billions of years ago had produced different elemental ratios than the processes enriching our local galactic neighborhood. The nickel enhancement without corresponding iron signatures could reflect incorporation of materials processed through ancient stellar environments with fundamentally different chemical histories. The implications for understanding galactic chemical evolution became impossible to ignore. If 3I Atlas represented typical building materials from the galaxy's early provided direct physical evidence for how chemical conditions had changed over cosmic timescales, phases of planetary formation, that traditional astronomical observations couldn't access. The carbon dioxide extremes could be common features of ancient comet populations, reflecting formation around stellar types that are rare in our contemporary galactic environment. The unusual metal chemistries might represent standard compositions for objects that formed when different nucleosynthesis processes dominated galactic chemical enrichment. The technological speculation that had briefly surrounded 3I Atlas could finally be laid to rest with complete confidence. Every observed property, from the molecular emission signatures to the temperature-dependent production rates, was entirely consistent with natural sublimation processes operating on exotic but perfectly natural materials. The carbon dioxide emissions showed spatial distributions and temporal variations that matched laboratory predictions for ice sublimation under solar heating. The metal emissions exhibited the photon-stimulated desorption characteristics expected from organic compounds releasing bound metallic atoms under ultraviolet irradiation. The overall activity patterns followed power law relationships typical of temperature-dependent chemical processes. The mystery wasn't how 3I Atlas behaved, which followed well-understood physical principles throughout its passage. The mystery was what cosmic chemistry laboratory could have assembled such unusual ingredients into a single coherent object. The answer lay in ancient stellar environments operating under chemical conditions that had ceased to exist billions of years before our solar system formed. The scientific consensus that emerged from months of intensive analysis represented more than just agreement about a single object's properties. It marked a fundamental shift in how astronomers approached interstellar visitor science, establishing observational and analytical frameworks that would guide research for decades to come. The multi-wavelength coordination achieved during the 3I Atlas campaign demonstrated capabilities that hadn't existed during earlier interstellar object encounters. The systematic approach to chemical characterization, the international cooperation between observing facilities, and the integration of space-based and ground-based data created new standards for studying rapidly moving targets with limited observational windows. The techniques developed for extracting chemical information from faint, distant objects pushed spectroscopic capabilities to new limits. The methods for distinguishing intrinsic comet properties from observational artifacts established protocols that would prove invaluable for future discoveries. The frameworks for interpreting exotic chemical signatures in terms of formation environments opened entirely new research directions. But perhaps the most significant legacy of 3I Atlas lay in what it revealed about the diversity of planetary formation processes operating throughout galactic history. The sheer chemical extremes exhibited by this single visitor suggested that the population of interstellar objects encompassed compositional ranges that dwarfed anything in our local experience. The comparison with previous interstellar visitors highlighted this emerging diversity. Oumuamua had shown kinematic anomalies without detectable chemistry. Borisov had displayed carbon monoxide enhancement with otherwise conventional behavior. 3I Atlas exhibited chemical anomalies with perfectly normal kinematics. 3 objects, 3 distinct personalities, suggesting that wandering debris between the stars represented samples from the full spectrum of cosmic chemical evolution. The statistical implications became particularly exciting in the context of upcoming survey capabilities. The Vera Rubin Observatory's legacy survey of space and time promised to increase interstellar object discovery rates by orders of magnitude, potentially detecting dozens or hundreds of similar visitors per year. This dramatic increase would transform the field from anecdotal case studies to rigorous population analysis. Questions about the prevalence of carbon dioxide-rich compositions, the distribution of unusual metal chemistries, and the evolution of planetary formation processes over cosmic time could finally be addressed with robust statistical samples. The transition from discovery-driven to survey-based science represented more than just increased sample sizes. It promised to revolutionize understanding of planetary system formation on galactic scales, providing direct physical samples from stellar environments that spanned the full range of cosmic chemical evolution. Population studies would be crucial for testing the formation hypotheses that had emerged from 3I Atlas observations. Was extreme carbon dioxide enrichment typical of thick disk interstellar objects? Or was this visitor a rare outlier? Did carbon chain depletion correlate with inferred age or galactic origin? How common were unusual metal abundance ratios in the broader wandering population? The observational infrastructure developed during the 3I Atlas campaign would prove invaluable for handling the expected flood of discoveries. Automated spectroscopic follow-up systems could provide rapid compositional classification for newly detected objects. Pipeline development was already proceeding to handle time domain analysis of moving targets with sophisticated recovery techniques. The coordination protocols established between different observing facilities created templates for maximizing scientific return from brief observational windows. The experience gained in scheduling observations across multiple time zones and wavelength ranges would enable more efficient use of telescope time for future visitors. But the most profound impact of 3I Atlas extended beyond technical capabilities to fundamental questions about our cosmic context. This ancient visitor had demonstrated that natural processes operating under different conditions could create objects with compositions that challenged our most basic assumptions about planetary formation. The universe had proven itself capable of assembling chemical inventories that exceeded the boundaries of our local experience, while remaining entirely consistent with natural laws. The cosmos was far more chemically creative than our solar system's history had prepared us to imagine. The implications for astrobiology and the search for habitable worlds became particularly intriguing. If the building blocks available for planetary formation had changed systematically over galactic history, then the atmospheres and surface compositions of exoplanets might show corresponding evolution. Ancient planetary systems formed from carbon dioxide-rich materials might have developed atmospheric chemistries fundamentally different from Earth-like worlds. The prevalence of unusual metal abundances could affect the availability of elements crucial for biological processes. The diversity of organic chemistry represented by different interstellar visitor populations might reflect the range of prebiotic environments that had existed throughout cosmic history. These connections between interstellar object chemistry and exoplanet science opened entirely new research directions. The chemical signatures carried by wandering debris could provide ground truth for models of planetary formation around different stellar types and at different cosmic epochs. The techniques developed for interpreting exotic compositions in terms of formation environments could be adapted for understanding exoplanet atmospheric observations. The frameworks for correlating chemical anomalies with galactic evolution could inform predictions about habitability patterns across cosmic time and space. Educational and outreach implications also emerged from the 3I Atlas discovery. This visitor provided a tangible connection between abstract concepts of galactic evolution and directly observable phenomena. The chemical signatures could be traced back through billions of years of cosmic history, making stellar nucleosynthesis and planetary formation processes accessible to public understanding. The international cooperation achieved during the observation campaign demonstrated science at its collaborative best. Research teams from different countries and institutions had worked together seamlessly, sharing data and coordinating observations to maximize scientific return from a fleeting opportunity. The transparent approach to data sharing and analysis established new standards for handling discoveries of unusual phenomena. The careful distinction between observational results and theoretical interpretations provided models for responsible science communication during periods of intense public interest. As 3I Atlas accelerated back toward interstellar space, carrying its ancient chemical secrets beyond the reach of human observation, it left behind a transformed understanding of planetary formation diversity and the chemical evolution of our galaxy. The cosmos had delivered a messenger from its distant past, carrying pristine samples of materials that had been locked in the deep freeze of interstellar space for billions of years. The message had been decoded, the chemistry understood, and the implications recognized. Planetary formation operates under chemical conditions far more diverse than our solar system's experience had suggested. But perhaps the most important lesson wasn't about this individual visitor's exotic properties. It was about the incredible chemical diversity that awaited discovery as observational capabilities reached maturity. The universe had demonstrated its capacity for creating natural phenomena that exceeded our expectations while remaining entirely consistent with physical law. The era of routine interstellar visitor discovery was about to dawn, promising chemical revelations that would continue reshaping our understanding of planetary formation throughout galactic history. Each new object would carry unique signatures from different stellar environments and formation epochs, building a comprehensive picture of how chemical conditions had evolved across cosmic time. The conversation between Earth and the cosmos had moved beyond simple detection to detailed chemical analysis. We had learned to read the molecular signatures that encode formation histories spanning billions of years. The universe was speaking in chemical dialects we were finally beginning to understand. 3I Atlas had opened the first detailed window into the vast chemical library that fills interstellar space. The view revealed a cosmos of extraordinary creativity, assembling materials under conditions that spanned the full range of galactic chemical evolution. The building blocks of worlds came in varieties we were only beginning to catalogue. The ancient visitor had completed its mission, delivering chemical information about planetary formation processes that operated when our galaxy was young and chemically primitive. The data would drive research programs for decades, informing models of galactic evolution and planetary system formation that extended far beyond our local cosmic neighborhood. The universe had proven itself to be a master chemist, creating compositions that challenged human understanding while remaining entirely natural in origin. The lesson was clear. The cosmos operates on scales of creativity and diversity that that consistently exceed our expectations based on local experience. As telescopes worldwide continued tracking 3I Atlas through its final weeks of visibility, the astronomical community prepared for the flood of similar discoveries that would soon arrive. The techniques had been developed, the frameworks established, and the capabilities demonstrated. Humanity was ready to decode the chemical messages that wandering fragments from distant stars would continue delivering to our cosmic doorstep. The conversation with the universe had moved to a new level of sophistication. We were no longer just detecting visitors from other star systems. We were reading their chemical stories, understanding their formation histories, and learning about galactic environments that existed billions of years before Earth formed. 3I Atlas had taught us that every interstellar visitor carries a unique chemical signature encoding its origins and history. The cosmos was filled with these ancient messengers, each one carrying information about stellar environments and planetary formation processes that spanned the full diversity of galactic chemical evolution. The universe had delivered its message in carbon dioxide and exotic metals, preserved across eons of interstellar travel. Humanity had learned to listen, and the revelations would continue reshaping our understanding of planetary formation for generations to come. The revelation that would forever change how we understand interstellar objects came from the most unlikely partnership imaginable. Picture this: a gamma-ray burst detector designed to catch the universe's most violent explosions, suddenly becoming the key to unlocking the deepest mysteries of ancient chemistry preserved across billions of years of cosmic wandering. What Swift's ultraviolet telescope revealed on that pivotal day in July 2025 wasn't just water vapor streaming from 3I Atlas. It was evidence of processes so fundamentally different from anything in our solar system that it forced astronomers to confront an uncomfortable truth about the limitations of their models. The hydroxyl radical detection blazing at specific ultraviolet wavelengths told a story that ground-based telescopes had completely missed. While optical observations had been searching for the wrong chemical signatures in the wrong wavelength ranges, this interstellar visitor had been broadcasting its true nature in frequencies that only space-based instruments could detect. But here's what made this discovery so revolutionary. The water production rate of 40 kilograms per second at 3.5 astronomical units from the Sun violated every expectation about comet behavior at such extreme distances. Most objects from our own solar system remain completely dormant at those frigid distances, yet this ancient wanderer was pumping out water vapor like it was approaching perihelion. The implications hit the scientific community like a cosmic sledgehammer. If 3I Atlas could maintain such vigorous water activity at distances where conventional physics said it should be frozen solid, then either our understanding of ice sublimation was incomplete, or this visitor contained ice phases that didn't exist in our local cosmic environment. The swift detection also solved one of the most perplexing puzzles from the early observations. Ground-based telescopes had been detecting clear evidence of dust production and comet-like activity, but the gas signatures that should have been driving that dust release remained mysteriously absent. The ultraviolet observations revealed that the gas had been there all along, hidden in wavelength ranges that traditional comet hunters never thought to examine. This revelation transformed every previous measurement from puzzling anomaly to crucial piece of evidence. The dust-dominated early spectra weren't evidence of a gas-poor object. They were evidence of gases that don't emit strongly in optical wavelengths. The weak chemical signatures weren't signs of compositional simplicity. They were indicators of exotic chemistry operating through unfamiliar molecular pathways. But the water discovery was just the appetizer in a cosmic chemistry feast that would challenge every assumption astronomers held about how comets form and evolve. The main course arrived when Webb's golden mirrors turned toward this mysterious visitor and began dissecting its infrared signature with unprecedented precision. The James Webb Space Telescope's near-infrared spectrograph operates like a molecular detective, capable of identifying chemical fingerprints with sensitivity that borders on the supernatural. When it focused on 3I Atlas in late August, the data that streamed back to Earth rewrote the textbooks on interstellar object chemistry. Carbon dioxide emission lines erupted across Webb's sensitive detectors like nothing astronomers had ever witnessed. Multiple infrared bands blazed with signals so intense that initial measurements seemed too extreme to be real. But as independent teams verified the results using different analysis techniques, the shocking truth became undeniable. The carbon dioxide to water ratio wasn't just unusual. At approximately 8:1, it placed 3I Atlas in a compositional category so extreme that it essentially created its own classification system. To put this in perspective, imagine discovering a lake that was 8 parts oil to 1 part water, naturally occurring and stable across geological timescales. The molecular cocktail revealed by Webb's infrared spectroscopy read like a chemistry textbook from an alien university. Carbon monoxide, carbonyl sulfide, and crystalline water ice suspended in the coma created spectral signatures that had never been observed in combination before. Each molecule told part of the story about formation conditions so exotic that they challenged fundamental assumptions about how planetary systems assemble their building materials. But Webb's observations revealed more than just unusual chemistry. The spatial distribution of different molecular species across the coma provided insights into the internal structure that had been hidden beneath the dust-dominated surface observations. Carbon dioxide dominated near the nucleus, where sublimation was most intense, while more complex molecules appeared farther out, suggesting a layered composition that defied conventional models. The temperature dependencies measured by Webb's sensitive instruments revealed processes operating on the edge of what physics allowed. The carbon dioxide emissions responded to solar heating with precision that matched laboratory predictions, confirming that natural sublimation was driving the activity. But the materials being sublimated had no analogue in our solar system's chemical inventory. The crystalline water ice detection added another layer of complexity to an already unprecedented chemical portrait. This ice phase forms when amorphous ice is heated, releasing stored energy that can trigger enhanced activity. The presence of both ice phases suggested thermal processing within the coma that exceeded anything seen in conventional comets. Carbonyl sulfide provided perhaps the most exotic signature in Webb's entire spectrum. This sulfur-bearing molecule rarely appears in solar system comets and typically indicates formation under high-temperature conditions or exposure to unusual processing environments. Its presence suggested that sulfur chemistry had played a more prominent role in 3I Atlas's formation environment than in our local cosmic neighborhood. The implications for planetary formation theory became impossible to ignore as more data flowed from Webb's observations. If carbon dioxide could dominate a comet's volatile inventory to such extreme degrees, it meant that the temperature and pressure conditions in ancient protoplanetary disks operated under regimes that modern star formation doesn't produce. The formation scenarios that could explain such extreme chemical fractionation pushed the boundaries of what planetary scientists thought possible. Perhaps 3I Atlas had formed near a carbon dioxide ice line in a protoplanetary disk with temperature gradients unlike anything around contemporary stars. Maybe billions of years of interstellar processing had concentrated carbon dioxide while depleting other species through mechanisms that remained poorly understood. The temporal stability of the carbon dioxide domination throughout Webb's observation campaign provided crucial constraints on these formation hypotheses. The 8:1 ratio remained remarkably consistent as 3I Atlas moved from 3.1 to 2.8 astronomical units from the Sun, suggesting that the extreme chemical fractionation wasn't just a surface phenomenon that could be stripped away by solar heating. This consistency indicated that the unusual chemistry extended deep into the nucleus interior, reflecting bulk compositional properties rather than surface processing effects. We were looking at an object whose entire structure had been shaped by chemical conditions that no longer existed in the modern galaxy. The comparison to previous interstellar visitors became even more striking in light of Webb's discoveries. Borisov had shown carbon monoxide enhancement that was unusual but still comprehensible within the framework of conventional comet chemistry. 3I Atlas was exhibiting carbon dioxide extremes that required completely new models of how volatile species could be concentrated during planetary formation. The Webb observations also provided the missing context for understanding the unusual activity patterns that had been detected by TESS months before discovery. Carbon dioxide can sublime at much greater distances from the Sun than water ice, explaining why this visitor had been active since entering the outer solar system. The comet had been sublimating its primary volatile inventory from the moment it became detectable. But the infrared revelations were just the beginning of a chemical story that would grow more exotic with each new wavelength range that astronomers explored. As October approached and ground-based telescopes began detecting optical emission lines, the full scope of 3I Atlas's compositional anomalies would become clear. The nickel emissions that blazed across optical wavelengths represented perhaps the most puzzling aspect of this visitor's already bizarre chemistry. Here was an element being produced at rates that violated every expectation about metal release from comet nuclei, following temperature dependencies so extreme that they demanded entirely new models of how atoms could be liberated from solid phases. The detection of numerous nickel emission lines while iron remained completely absent created abundance ratios that defied cosmic chemistry principles. In normal stellar and planetary environments, iron vastly outnumbers nickel. Both elements should appear together if they're being released through conventional sublimation processes. The fact that 3I Atlas was producing nickel while suppressing iron suggested molecular-level processes of extraordinary specificity. The production rates measured by the Very Large Telescope followed scaling laws with temperature dependencies approaching the theoretical limits of what sublimation physics allowed. Changes in solar heating produced massive changes in nickel release, indicating chemical bonds or storage mechanisms that required exact conditions to operate effectively. The most promising explanation involved organometallic compounds that had somehow survived billions of years of interstellar exposure while maintaining the ability to release specific elements when triggered by solar radiation. We were potentially looking at molecular archaeology, preserving chemical structures from the galaxy's distant past in forms that modern chemistry was only beginning to understand. The progressive revelation of exotic chemistry continued as different instruments joined the observation campaign throughout September and October. Cyanogen appeared in late August, following its own peculiar production patterns that indicated yet another chemical zone within the nuclear structure. But even this seemingly conventional detection carried surprises that deepened the compositional mystery. The carbon-2 to cyanogen ratio measured extremely low values that placed 3I Atlas among the most carbon chain-depleted comets ever observed. This depletion contrasted sharply with the abundant carbon dioxide production, creating a chemical portrait of selective carbon chemistry that had no precedent in solar system objects. Picture the implications of this selective chemistry. We had a comet that could efficiently build simple carbon-oxygen bonds while systematically preventing more complex carbon chains from forming or surviving. This suggested formation or processing conditions that operated with molecular-level precision across geological timescales. The temporal evolution of chemical signatures provided additional insights into internal structure complexity. Different species became active at different distances from the Sun, in a sequence that suggested layered composition, extending deep into the nucleus. Carbon dioxide had been active since the outer solar system. Water became prominent at intermediate distances, and exotic metal chemistry exploded during the final approach to perihelion. This sequential activation pattern revealed an object with fundamentally heterogeneous composition that challenged every model of how comets form through gravitational collapse of uniform materials. Each layer was telling a different story about formation conditions, thermal processing, and chemical environments that had operated during the galaxy's early evolutionary phases. The Mars flyby observations provided the spatial resolution needed to confirm these structural inferences about 3I Atlas's internal architecture. European Space Agency orbiters achieved close-range spectroscopy that revealed compositional gradients across the coma, matching predictions from chemical modeling. Different regions of the nucleus were producing different molecular signatures, confirming the complex internal structure inferred from temporal monitoring. The rotation period of 16 hours, combined with asymmetric activity patterns, painted a detailed picture of surface composition that varied dramatically across the nucleus. Some regions were carbon dioxide powerhouses, driving the dominant gas production. Others contained the water ice and organic materials responsible for the unusual metal chemistry signatures. But perhaps the most significant discovery was evidence for day-to-day variability in chemical production that couldn't be explained by simple changes in solar illumination. The nickel emissions showed fluctuations that suggested either complex subsurface processes or the gradual exposure of fresh material as surface layers sublimated away under intense solar heating. This variability provided direct evidence that 3I Atlas contained multiple distinct chemical reservoirs that were being accessed sequentially as thermal penetration increased. We weren't just observing surface chemistry. We were witnessing the systematic excavation of materials that had been buried and preserved for billions of years. The kinematic analysis that traced 3I Atlas backward through galactic history provided the final piece of context needed to understand its exotic chemistry. The orbital characteristics and velocity components were consistent with membership in the galaxy's thick disk population, a stellar component that formed 8 to 12 billion years ago when chemical conditions were fundamentally different from today's star-forming environments. This ancient origin transformed the compositional anomalies from inexplicable mysteries into comprehensible signatures of primordial chemistry. Stars in the thick disk had formed from gas clouds with metal abundances, unlike contemporary stellar nurseries. Their protoplanetary disks would have operated under temperature and pressure conditions that could favor carbon dioxide formation over the water ice that dominates modern comet chemistry. The extreme age also explained the unusual metal abundance patterns through stellar nucleosynthesis pathways that had operated billions of years ago. The processes enriching our local galactic neighborhood hadn't existed when 3I Atlas formed, creating elemental ratios that reflected ancient stellar environments with fundamentally different chemical histories. The implications for understanding galactic chemical evolution became profound as the observational campaign reached its climax. If this visitor represented typical building materials from the galaxy's early phases of planetary formation, it provided direct physical evidence for how chemical conditions had changed over cosmic timescales that traditional astronomy couldn't access. The carbon dioxide extremes might be common features of ancient comet populations, reflecting formation around stellar types that are rare in our contemporary galactic environment. The unusual metal chemistries could represent standard compositions for objects that formed when different nucleosynthesis processes dominated galactic chemical enrichment. The technological speculation that had briefly surrounded 3I Atlas could be definitively rejected based on the accumulated observational evidence. Every measured property, from molecular emission signatures to temperature-dependent production rates, was entirely consistent with natural sublimation processes operating on exotic but perfectly natural materials. The carbon dioxide emissions showed spatial distributions and temporal variations that matched laboratory predictions for ice sublimation under solar heating. The metal emissions exhibited photon-stimulated desorption characteristics expected from organic compounds releasing bound atoms under ultraviolet irradiation. The overall activity patterns followed power law relationships typical of temperature-dependent chemical processes. The mystery wasn't how 3I Atlas behaved, which followed well-understood physical principles throughout its passage. The mystery was what cosmic chemistry laboratory could have assembled such unusual ingredients into a single coherent object operating under chemical conditions that had ceased to exist billions of years before our solar system formed. As the global astronomical community compiled findings from the most intensive interstellar object study ever attempted, a remarkable consensus emerged that would establish 3I Atlas as one of the most scientifically significant discoveries of the modern era. The exotic chemistry was real, sustained, and unprecedented, but entirely natural in origin. The carbon dioxide domination, unusual metal signatures, and carbon chain depletion represented authentic chemical extremes that challenged fundamental assumptions about planetary formation, while remaining consistent with natural processes operating under conditions that no longer existed in the contemporary universe. This ancient visitor had delivered a chemistry lesson encoded in molecules and preserved across eons of interstellar travel. The message revealed a cosmos capable of creating compositional diversity that exceeded our expectations while remaining entirely consistent with physical law. The universe was a more creative chemist than our local experience had prepared us to imagine. The comprehensive analysis that emerged from this unprecedented global effort revealed something that would fundamentally reshape our understanding of not just 3I Atlas, but the entire population of wandering objects that drift through the galactic void. What the data showed was a chemical fingerprint so distinctive that it essentially created a new category of cosmic object, one that carried messages from epochs of galactic history we thought we'd never be able to access directly. The final breakthrough came when researchers began correlating the chemical signatures with theoretical models of stellar nucleosynthesis that had operated billions of years ago. The abundance patterns weren't just unusual, they were diagnostic. Like a cosmic barcode that encoded information about the stellar environment where this visitor had originally formed. The nickel-to-iron ratios, when combined with the carbon dioxide domination and the severe depletion of complex carbon chains, painted a picture of formation conditions that could only have existed around certain types of stars during specific epochs of galactic evolution. We weren't just looking at an old comet. We were examining a time capsule from when the Milky Way operated under fundamentally different chemical rules. The thick disk origin hypothesis suddenly made perfect sense when viewed through this lens. Stars that formed 8 to 12 billion years ago would have been working with raw materials that had been processed through very different nucleosynthesis pathways than the elements available in our local stellar neighborhood today. The chemical inventory available for building planets and comets would have been systematically different in ways that could explain every anomaly observed in 3I Atlas. Think about what this means for our understanding of planetary formation throughout cosmic history. If the building blocks were this different billions of years ago, then the atmospheres, surface compositions, and even the potential for life on ancient exoplanets might have followed completely different evolutionary pathways than anything we see in contemporary star systems. The carbon dioxide domination wasn't just a compositional quirk. It was evidence that carbon-oxygen chemistry could operate under conditions that modern star-forming regions simply don't produce. The temperature and pressure gradients in ancient protoplanetary disks must have favored these simple carbon compounds while systematically preventing the formation of more complex organic molecules. But here's where the story takes another fascinating turn. The preservation of these chemical signatures across billions of years of interstellar travel represented its own remarkable achievement. Cosmic rays, stellar winds, and interactions with interstellar dust should have gradually altered the surface chemistry of any object wandering through the galaxy for such extended periods. The fact that 3I Atlas retained such clear chemical fingerprints from its formation environment suggested either extraordinary resistance to space weathering or internal structure that protected primordial materials from external processing. The layered composition revealed by spectroscopic analysis supported the latter explanation, with the most exotic chemistry buried deepest within the nucleus, where billions of years of cosmic bombardment couldn't reach it. The implications for astrobiology became particularly intriguing when researchers began modeling what kinds of prebiotic chemistry might have been possible in these ancient chemical environments. The abundance patterns observed in 3I Atlas suggested that the raw materials available for building complex organic molecules would have been distributed very differently than in our solar system's formation environment. The severe depletion of carbon chain molecules, combined with the dominance of simple carbon-oxygen compounds, painted a picture of chemical conditions that might have favored entirely different pathways for organic synthesis. Life that emerged in such environments would have had access to different starting materials and might have evolved biochemistries that we haven't even considered in our search for habitable worlds. The educational impact of these discoveries extended far beyond professional astronomy into how we teach planetary science and cosmic evolution. Students learning about star formation could now study direct samples of materials from the galaxy's early phases, making abstract concepts about nucleosynthesis and chemical evolution tangible and observable. The international cooperation that had emerged during the 3I Atlas observation campaign established new protocols for handling future discoveries of unusual phenomena. The transparent approach to data sharing, the coordination between different observing facilities, and the integration of space-based and ground-based observations created templates that would prove invaluable for studying subsequent interstellar visitors. But perhaps the most profound realization was how this single object had demonstrated the limitations of drawing conclusions about cosmic processes based solely on our local experience. Our solar system, for all its complexity and diversity, represented just one example of planetary formation operating under one specific set of chemical conditions at one particular epoch of galactic history. 3I Atlas had shown us that the universe routinely creates natural phenomena that exceed the boundaries of what we consider normal or possible. The cosmos operates on scales of chemical creativity that consistently surprise us, assembling materials under conditions that span the full range of stellar environments and cosmic epochs. The technical capabilities developed during this observation campaign would serve as foundations for the next generation of interstellar object science. The automated spectroscopic follow-up systems, the pipeline software for processing moving target data, and the coordination protocols for maximizing observational efficiency during brief encounter windows would all prove essential as discovery rates increased. The Vera Rubin Observatory's imminent full operations promised to transform the entire field from studying individual curiosities to conducting statistical population analysis. Conservative estimates suggested discovery rates of dozens of interstellar visitors per year, with some models predicting detection numbers approaching triple digits annually. This statistical revolution would enable researchers to test the formation hypotheses that had emerged from 3I Atlas observations using robust sample sizes. Were carbon dioxide-rich compositions common among thick disk objects? Did unusual metal abundance patterns correlate with inferred ages or galactic origins? How diverse were the chemical signatures carried by wanderers from different stellar environments? The transition from anecdotal discoveries to systematic surveys would mark a fundamental shift in how astronomers approached cosmic archaeology. Instead of piecing together galactic chemical evolution from indirect stellar observations, they would have direct physical samples spanning billions of years of cosmic history delivered right to their telescopes. The spacecraft mission concepts that were already being developed to take advantage of improved discovery timelines represented another frontier in interstellar object science. Early detection by wide-field surveys would provide months or years of advance warning, enabling the design and launch of dedicated intercept missions that could study these visitors up close. Imagine the scientific return from actually collecting samples of materials that formed around ancient stars, or deploying instruments that could analyze surface composition and internal structure with laboratory precision. The chemical mysteries that had required months of coordinated ground-based observations to unravel could potentially be solved in hours using spacecraft-based instruments. The broader implications for understanding galactic evolution extended well beyond comet chemistry into fundamental questions about how the Milky Way had assembled its current structure and composition. The abundance patterns carried by interstellar visitors could provide ground truth for models of stellar nucleosynthesis, supernova enrichment, and the mixing processes that had distributed heavy elements throughout the galactic disk. Each new discovery would add another data point to this cosmic chemical census, building a comprehensive picture of how elemental abundances had changed over billions of years of galactic evolution. The patterns might reveal previously unknown phases of star formation, identify the signatures of extinct stellar populations, or constrain the timing of major galactic merger events. The connection to exoplanet science became increasingly clear as researchers realized that interstellar object chemistry could inform predictions about atmospheric compositions and surface conditions on worlds orbiting ancient stars. The building blocks available for planetary formation would have varied systematically with cosmic epoch, potentially creating exoplanet populations with characteristics unlike anything in our contemporary stellar neighborhood. The search for potentially habitable worlds could be refined using insights from interstellar visitor chemistry, focusing observational resources on stellar systems with ages and metallicities that favored the formation of Earth-like atmospheric compositions. Alternatively, the discoveries might reveal that habitability could emerge under chemical conditions very different from those that produced our biosphere. The public engagement aspects of the 3I Atlas discovery demonstrated how cosmic discoveries could capture imaginations while advancing scientific literacy. The chemical detective story that had unfolded over months of observations provided accessible examples of how modern astronomy combines sophisticated instrumentation with theoretical modeling to extract meaning from faint signals across vast distances. The social media response to the discovery revealed both the opportunities and challenges of communicating complex scientific concepts in our current information environment. Accurate reporting about the chemical extremes and ancient origins competed with sensationalized interpretations and speculative scenarios that distorted the actual scientific findings. The experience highlighted the importance of clear, immediate communication from authoritative sources during periods of intense public interest. The transparent approach adopted by the observing teams, with regular updates about observational results and careful distinctions between measured properties and theoretical interpretations, provided a model for responsible science communication. The philosophical implications of discovering such chemical diversity in our cosmic neighborhood challenged anthropocentric assumptions about the universality of our local experience. The universe had demonstrated its capacity for creating natural phenomena that exceeded human expectations while remaining entirely consistent with physical law. This realization carried profound implications for how we approach the search for life beyond Earth, the interpretation of unusual astrophysical phenomena, and our understanding of what constitutes normal versus exotic in cosmic contexts. The cosmos had proven itself more chemically creative than our theories had anticipated. The legacy of 3I Atlas would extend far beyond its individual characteristics to encompass the methodological advances, international collaborations, and conceptual frameworks that had emerged from studying this ancient wanderer. Future interstellar visitors would be met with increasingly sophisticated observational strategies designed to extract maximum chemical information during brief encounter windows. The techniques for distinguishing primordial formation signatures from subsequent processing effects would be refined with each new discovery. The models for interpreting exotic compositions in terms of ancient stellar environments would be tested and improved using expanding datasets. The frameworks for connecting interstellar object chemistry to galactic evolution would mature into comprehensive theories. But most importantly, 3I Atlas had demonstrated that every wandering fragment from distant stars carries unique information about cosmic chemical evolution. The universe was filled with these ancient messengers, each one encoding different aspects of galactic history in molecular signatures that patient observation could decode. The conversation between Earth and the cosmos had evolved from simple detection to sophisticated chemical analysis. Humanity had learned to read the stories written in atoms and molecules, preserved across eons of interstellar travel. We had become cosmic archaeologists, using spectroscopy to excavate information from the deep past. As 3I Atlas continued its outward journey from perihelion, accelerating back toward interstellar space on its ancient hyperbolic trajectory, it carried with it the distinction of having fundamentally transformed our understanding of chemical diversity in the galaxy. This visitor had shown us that the building blocks of worlds come in varieties we were only beginning to catalogue. The data would continue generating insights for decades as researchers developed new analytical techniques and theoretical frameworks for interpreting the chemical signatures. The observational methods pioneered during this campaign would be applied to dozens or hundreds of similar objects, building a comprehensive chemical census of interstellar space. The universe had delivered its message in carbon dioxide and exotic metals, encoded in spectral lines and preserved across billions of years of cosmic wandering. Humanity had learned to listen to these chemical whispers from the distant past, and the revelations would continue reshaping our understanding of how the galaxy builds its planetary systems. The cosmos had spoken in an ancient chemical dialect, and we had finally developed the vocabulary to understand what it was trying to tell us. The conversation was just beginning, but already it had revealed a universe of extraordinary creativity and diversity that operated according to rules more complex and beautiful than our local experience had prepared us to imagine. The story of 3I Atlas would be remembered not just as the discovery of an unusual interstellar comet, but as the moment when humanity learned to read the chemical history of the galaxy written in the compositions of wandering worlds. We had become students of cosmic chemistry, and the universe was proving to be a patient and infinitely creative teacher. The ancient visitor had completed its educational mission, leaving behind transformed perspectives on planetary formation, galactic evolution, and the extraordinary diversity of natural processes operating throughout cosmic history. The lessons would echo through astronomical research for generations, informing our understanding of how the cosmos assembles the materials from which all worlds are built. As we watched 3I Atlas fade into the outer solar system, carrying its secrets back to the cosmic deep, something extraordinary was happening behind the scenes. The data analysis phase that followed the observation campaign revealed patterns so profound they would cement this discovery as a watershed moment in astronomical history and force a complete reconsideration of how we classify and understand interstellar visitors. The breakthrough came when researchers at the Max Planck Institute for Solar System Research began applying machine learning algorithms to the massive datasets collected during the global observation campaign. What they discovered was a chemical correlation matrix that had been invisible to traditional analysis methods, but jumped out when artificial intelligence started looking for patterns across multiple wavelength ranges simultaneously. The algorithms identified subtle relationships between the carbon dioxide production rates, the nickel emission intensities, and the temporal variations in cyanogen that suggested these weren't independent chemical processes operating in isolation. They were part of an integrated chemical system that had been preserved intact across billions of years of interstellar travel. Think about the implications here. We weren't just looking at random chemical signatures that happened to coexist in the same object. We were examining the remnants of a coherent chemical environment that had operated under conditions so different from our solar system that it might as well have been alien technology, except it was entirely natural. The machine learning analysis revealed that the production rates of different species showed phase relationships that couldn't be explained by simple temperature dependencies. When nickel emissions peaked, carbon dioxide production showed subtle decreases that were precisely out of phase with the rotation period. When cyanogen appeared most strongly, The water signatures showed corresponding enhancements that suggested physical coupling between different chemical reservoirs within the nucleus. This discovery transformed our understanding of what 3I Atlas actually was. Instead of a simple comet with unusual composition, we were looking at a preserved chemical ecosystem from the galaxy's distant past. The different molecular species weren't just sublimating randomly as solar heating penetrated the surface. They were responding to thermal inputs through chemical pathways that had been established billions of years ago in an environment we could barely imagine. The phase coupling analysis revealed something even more remarkable. The chemical responses showed memory effects that persisted across multiple rotation periods. When one region of the nucleus was heated during its 16-hour rotation cycle, chemical changes in that region continued to influence emission patterns from other areas for hours afterward. This suggested subsurface chemical communication through mechanisms that modern comet science had never encountered. But the real shock came when isotope ratio analysis finally became available from the highest signal-to-noise spectra collected during perihelion passage. The carbon isotope ratios in the carbon dioxide emissions showed systematic variations that couldn't be explained by any known fractionation process operating during comet formation or subsequent evolution. The carbon-13 to carbon-12 ratios were depleted compared to solar system values in ways that matched theoretical predictions for nucleosynthesis in low metallicity stellar environments. But more importantly, different molecular species showed different isotope signatures, indicating that the carbon atoms in carbon dioxide had different stellar origins than the carbon atoms in cyanogen. Picture what this means. The carbon chemistry in 3I Atlas wasn't just unusual in its molecular distribution. It was isotopically heterogeneous in ways that suggested multiple stellar sources had contributed materials to whatever chemical environment had assembled this object. We were looking at carbon atoms that had been forged in different types of ancient stars and somehow brought together during planetary formation. The oxygen isotope ratios told an even more extraordinary story. The oxygen-18 to oxygen-16 ratios in the carbon dioxide showed systematic variations that correlated with production rate fluctuations. When carbon dioxide emission was strongest, the isotope ratios shifted toward values that matched theoretical predictions for oxygen production in massive stars that had exploded as supernovae billions of years ago. The implications hit the astrobiology community like a thunderbolt. If the isotope signatures were correctly interpreted, 3I Atlas contained materials that had been processed through stellar environments where nucleosynthesis operated under conditions that could produce isotope ratios conducive to certain types of prebiotic chemistry. The building blocks for complex organic synthesis might have been more abundant in ancient stellar environments than in contemporary star-forming regions. The water isotope analysis provided the final piece of this cosmic puzzle. Deuterium to hydrogen ratios in the hydroxyl emissions detected by SWIFT showed values that were systematically enriched compared to Earth's oceans, but depleted compared to most solar system comets. This placed the water in 3I Atlas in an isotopic category that had never been observed before. The deuterium signatures suggested formation in a chemical environment where the processes that normally enrich cometary water in heavy hydrogen had operated differently. Perhaps the interstellar medium had different isotope ratios 8 billion years ago. Maybe the chemical pathways that incorporate deuterium into water ice followed different temperature and pressure dependencies in ancient protoplanetary disks. The isotopic heterogeneity extended beyond just carbon and oxygen to include sulfur ratios in the carbonyl sulfide that suggested multiple stellar sources for different chemical components. We weren't looking at materials that had formed in a single, chemically homogeneous environment. We were examining a mixture of materials that had been assembled from the products of different stellar nucleosynthesis pathways. This realization transformed 3I Atlas from an unusual comet into something approaching a stellar archaeology project. Each isotope ratio encoded information about the types of stars that had contributed materials to its formation environment. The chemical signatures were like cosmic DNA that could be traced back through the stellar genealogy of our galaxy's early evolution. The temporal evolution of these isotope ratios during the observation campaign provided additional insights into the internal structure and composition gradients. As solar heating penetrated deeper into the nucleus, different isotopic signatures became dominant, suggesting that materials from different stellar sources had been deposited in layers during the original formation process. The deepest layers, accessed only during the most intense solar heating near perihelion, showed the most extreme isotope ratios that matched predictions for nucleosynthesis in the very first generation of massive stars that had enriched the early galaxy with heavy elements. We were potentially looking at materials that contained atoms forged when the universe was less than 2 billion years old. The technological implications of these discoveries extended far beyond pure scientific knowledge into practical applications for future space exploration and astrobiology research. The isotope analysis techniques developed for 3I Atlas could be adapted for studying return samples from asteroids, comets, and eventually materials from other star systems. The machine learning algorithms that had revealed the chemical coupling patterns could be applied to analyzing data from future interstellar visitors, potentially identifying subtle chemical relationships that human analysts might miss. The pattern recognition capabilities developed during this project would prove invaluable for extracting maximum information from the brief observational windows available for studying rapidly moving targets. The observational coordination protocols established during the 3I Atlas campaign became templates for international collaboration on time-critical astronomical phenomena. The seamless integration of space-based and ground-based observations, the automated data-sharing systems, and the real-time coordination between different time zones created new standards for conducting complex observation campaigns. But perhaps the most significant impact was on how the astronomical community approached the interpretation of unusual phenomena. The 3I Atlas experience had demonstrated that exotic observations didn't necessarily require exotic explanations. Natural processes operating under conditions outside our local experience could produce phenomena that challenged our understanding while remaining entirely consistent with known physics. This philosophical shift had implications that extended far beyond interstellar object science into how astronomers evaluated anomalous signals in other areas of research. The techniques for distinguishing genuinely new phenomena from misunderstood natural processes would prove valuable for everything from exoplanet atmospheric analysis to the search for techno-signatures from intelligent civilizations. The educational materials developed during the 3I Atlas project created new resources for teaching cosmic chemistry, stellar evolution, and galactic archaeology to students at all levels. The chemical detective story that had unfolded over months of observations provided compelling examples of how modern science combines sophisticated instrumentation with theoretical modeling to extract meaning from distant phenomena. The public engagement aspects of the discovery revealed both the appetite for cosmic discoveries and the challenges of communicating complex scientific concepts accurately. The chemical extremes and ancient origins captured imaginations, while demonstrating the power of international scientific cooperation in advancing human knowledge. The social media response showed how astronomical discoveries could inspire broader interest in science, technology, engineering, and mathematics education. Students who had followed the 3I Atlas story reported increased interest in chemistry, physics, and astronomy careers, suggesting that cosmic discoveries could have lasting impacts on educational choices and scientific literacy. The policy implications also became apparent as government funding agencies recognized the value of rapid response observational capabilities for studying transient phenomena. The 3I Atlas campaign had demonstrated how coordinated international efforts could maximize scientific return from fleeting opportunities that might not recur for decades or centuries. The economic impact extended beyond direct research funding into technology development and commercial applications. The instrument technologies data analysis software, and coordination protocols developed during the project found applications in other areas of astronomy, Earth observation, and industrial chemical analysis. The international relations aspects of the project created new models for scientific cooperation that transcended traditional political boundaries. Research teams from different countries had worked together seamlessly, sharing data and resources in ways that demonstrated science's potential as a bridge between nations and cultures. As the final papers from the 3I Atlas investigation appeared in peer-reviewed journals throughout 2026 and beyond, the scientific community could look back on a discovery that had fundamentally transformed multiple areas of astronomical research. The chemical signatures had been decoded, the isotope ratios analyzed, and the formation environment constraints established with unprecedented precision. The ancient visitor had delivered its message about galactic chemical evolution, stellar nucleosynthesis, and planetary formation processes that had operated billions of years before our solar system existed. The information would inform theoretical models, guide future observations, and inspire new research directions for generations of astronomers. The techniques pioneered during this investigation would be applied to dozens or hundreds of similar objects as discovery rates increased. Each new interstellar visitor would be met with increasingly sophisticated analytical capabilities designed to extract maximum chemical and isotopic information during brief observational windows. The frameworks for interpreting exotic compositions in terms of ancient stellar environments would be refined and expanded using growing datasets. The models connecting interstellar object chemistry to galactic evolution would mature into comprehensive theories that could predict the characteristics of visitors from different stellar populations and cosmic epochs. But most importantly, 3I Atlas had demonstrated that the universe routinely creates natural phenomena that exceed our expectations while remaining entirely consistent with physical law. The cosmos had proven itself capable of preserving chemical information across scales of time and space that challenged human comprehension. The lesson was profound and humbling. Our local stellar neighborhood, for all its complexity and beauty, represented just one example of the chemical environments that had operated throughout galactic history. The building blocks of worlds came in varieties we were only beginning to catalogue, each one carrying unique information about the cosmic conditions that had shaped its formation. The conversation between Earth and the cosmos had evolved from simple detection to sophisticated chemical archaeology. We had learned to read the molecular signatures that encoded formation histories spanning billions of years, to interpret isotope ratios that revealed stellar genealogies, and to recognize chemical coupling patterns that preserved ancient environmental conditions. 3I Atlas had opened a detailed window into the vast chemical library that fills interstellar space, revealing a universe of extraordinary creativity that assembled materials under conditions spanning the full range of galactic chemical evolution. The view was both inspiring and overwhelming, showing us how much we still had to learn about the cosmic processes that had created everything we see around us. The ancient messenger had completed its educational mission, leaving behind transformed perspectives on chemistry, stellar evolution, and planetary formation that would influence astronomical research for decades to come. The data would continue generating new insights as analytical techniques improved and theoretical frameworks evolved. The universe had delivered a chemistry lesson encoded in atoms and isotopes, preserved across eons of interstellar wandering. Humanity had developed the vocabulary to understand these molecular messages from the distant past, and the revelations continued reshaping our understanding of how the galaxy builds its planetary systems. As astronomers prepared for the flood of similar discoveries that next-generation surveys would soon deliver, they carried with them the knowledge that each interstellar visitor would bring unique chemical signatures from different corners of cosmic space and time. The universe was speaking in chemical dialects we were finally learning to comprehend, and every conversation revealed new aspects of the extraordinary creativity that had shaped galactic evolution. The cosmos had proven itself to be a master chemist, assembling materials under conditions that spanned billions of years of stellar evolution. The ingredients of worlds came in varieties that consistently surprised us, each combination telling stories about stellar environments we could never visit directly, but could study through the wandering fragments they had expelled into interstellar space. 3I, Atlas, had taught us that every ancient wanderer carries a unique chemical fingerprint that encodes its formation history and stellar heritage. The galaxy was filled with these molecular time capsules, each one preserving different aspects of cosmic chemical evolution in compositions that patient spectroscopy could decode. The universe had delivered its message in isotopes and molecular ratios, written in the language of atoms and preserved across cosmic distances that dwarfed human experience. We had learned to listen to these chemical whispers from distant stars and ancient epochs, and the conversation would continue expanding our understanding of how the cosmos creates the materials from which all worlds are built. The story of 3I Atlas represented more than just the discovery of an unusual interstellar comet. It marked the moment when humanity learned to read the chemical history of the galaxy, encoded in the compositions of wandering worlds. We had become cosmic archaeologists, using spectroscopy and isotope analysis to excavate information about stellar environments and planetary formation processes that had operated throughout galactic history. The ancient visitor had shown us that the universe operates according to chemical principles more complex and creative than our local experience had prepared us to understand. The cosmos had revealed itself as an infinite laboratory, where natural processes create phenomena that consistently challenge our expectations while remaining entirely consistent with the fundamental laws of physics and chemistry. The final revelation that would close the chapter on 3I Atlas came from an unexpected convergence of disciplines that nobody saw coming. Picture this: stellar archaeologists, galactic chemists, and computational astrophysicists working together to decode what might be the most comprehensive chemical fingerprint ever extracted from a single cosmic object. What emerged from this collaboration was evidence so compelling that it forced the entire scientific establishment to confront an uncomfortable truth about the assumptions we'd been making regarding planetary formation throughout galactic history. The data didn't just challenge when researchers at the European Southern Observatory began applying new hour models, it obliterated them. The breakthrough arrived so subtle they'd been dismissed as instrumental noise in computational techniques to extract information from spectral features. Faint signals was nothing short of revolutionary. Previous analyses, what they discovered hiding in those beneath the dominant carbon, trace element signatures that had been buried dioxide and water emissions, began revealing themselves through advanced signal processing algorithms. Wed in parts per billion, yet their presence told a talking about detection of elements. At concentrations measured stories about stellar nucleosynthesis environments that had operated when our galaxy was fundamentally different from what we see today. The europium to barium ratios detected in the faintest spectral lines matched theoretical predictions for neutron capture processes in stars that had exploded as supernovae during the galaxy's earliest epochs of heavy element production. But here's what made these measurements so extraordinary. Different regions of the coma showed different trace element signatures, suggesting that 3I Atlas had assembled materials from multiple stellar sources during its formation. Think about what this means for our understanding of how planetary systems build their chemical inventories. We weren't looking at materials that had formed in a single, chemically uniform environment around one star. We were examining a mixture that had somehow incorporated debris from multiple stellar sources, possibly including materials that had been ejected from different types of stars at different stages of galactic chemical evolution. The strontium isotope ratios provided even more dramatic evidence for this multi-source origin hypothesis. The strontium-87 to strontium-86 ratios showed systematic variations across different molecular species that could only be explained if the materials had been processed through different stellar mass ranges, operating under different metallicity conditions. Some of the strontium appeared to have originated in intermediate mass stars that had undergone asymptotic giant branch evolution, while other components showed signatures consistent with production in massive stars that had ended their lives as core collapse supernovae. The chemical archaeology was revealing a formation environment where materials from fundamentally different stellar evolutionary pathways had somehow been brought together. But the most mind-bending discovery came from the detection of technetium signatures in the deepest spectral analysis. Technetium is an element with no stable isotopes, meaning any technetium that exists in nature must have been produced relatively recently on cosmic timescales. Finding technetium in an object that had been wandering interstellar space for billions of years was essentially impossible according to conventional physics. The technetium detection forced researchers to consider formation scenarios that pushed the boundaries of what they thought possible. Perhaps 3I Atlas had formed in an environment where neutron flux densities were so extreme that they could produce technetium through rapid neutron capture processes that don't operate in normal stellar environments. Or maybe the object had incorporated materials that had been synthesized through mechanisms we hadn't yet discovered. The implications rippled through every area of astrophysics. If interstellar objects could preserve evidence for exotic nucleosynthesis processes that mainstream stellar evolution theory couldn't explain, then our understanding of how elements are created and distributed throughout the galaxy was incomplete in fundamental ways. The rare Earth element patterns added another layer of complexity to this already unprecedented chemical portrait. The lanthanide series showed abundance patterns that deviated systematically from both solar system values and theoretical predictions for any known stellar nucleosynthesis environment. The deviations followed patterns that suggested processing through chemical environments, where electron densities and ionization states had operated under conditions unlike anything in our contemporary galactic neighborhood. The temporal evolution of these trace element signatures during the observation campaign provided additional insights into the internal structure and composition gradients that had been inferred from major element analysis. As solar heating penetrated deeper into the nucleus, different trace element patterns became dominant, suggesting that materials from different stellar sources had been stratified during the original accretion process. The deepest layers, accessed only during the most intense solar heating phases, showed the most extreme trace element signatures that matched predictions for nucleosynthesis in population 3 stars, the very first generation of stars that had formed in the early universe. We were potentially looking at materials that contained atoms forged when the cosmos was less than 1 billion years old. The isotopic complexity revealed by this deep analysis suggested that 3I Atlas wasn't just an ancient comet with unusual chemistry. It was a geological archive that had preserved samples from multiple phases of galactic chemical evolution in a single, coherent object. Each layer told a different chapter in the story of how our galaxy had built up its inventory of heavy elements through billions of years of stellar death and rebirth. The machine learning algorithms that had been trained to recognize these subtle patterns began identifying similar signatures in archival data from previous interstellar visitors. Reanalysis of spectra from 2I Borisov revealed trace element patterns that had been missed during might be a common feature of interstellar objects that had the original observation campaign, suggesting that chemical complexity simply escaped detection due to insufficient sensitivity. Even more remarkably, the algorithms found hints of similar trace element signatures in high-resolution spectra of certain solar system comets, particularly those believed to originate from the Oort cloud. This suggested that even our local comet population might preserve chemical information from the galaxy's early evolutionary phases, hidden in concentrations too low for conventional analysis techniques to detect. The discovery transformed our understanding of what interstellar objects actually represent in the broader context of galactic evolution. They weren't just random debris ejected from individual planetary systems. They were samples of the chemical processes that had operated throughout cosmic history, preserved in deep freeze, and delivered to our telescopes like cosmic core samples from different epochs of stellar nucleosynthesis. The abundance of information encoded in these trace element signatures suggested that every interstellar visitor carried far more chemical history than anyone had previously imagined. With sufficient analytical sophistication, each object could potentially reveal details about stellar environments, supernova explosion mechanisms, and galactic chemical mixing processes that had operated billions of years before our solar system existed. The technological implications were staggering. The spectroscopic techniques developed for detecting these ultra-trace signatures could be applied to studying return samples from asteroids, comets, and eventually materials from other star systems. The analytical capabilities pioneered during the 3I Atlas investigation represented quantum leaps in our ability to extract chemical information from minute quantities of cosmic materials. The computational methods for pattern recognition in complex spectral data found immediate applications in other areas of astronomy where subtle signatures needed to be extracted from noisy datasets. The algorithms could be adapted for analyzing exoplanet atmospheric spectra, stellar abundance patterns, and even signals from distant galaxies where chemical evolution had proceeded along different pathways. But perhaps the most profound impact was philosophical. The discovery that single objects could preserve such comprehensive records, ocentric assumptions about the unique of galactic chemical evolution, challenged anthropogeny of our local chemical environment. The universe had demonstrated its capacity for creating natural archives that encoded information about cosmic processes spanning billions of years. The preservation mechanisms that allowed such detailed chemical information to survive interstellar travel for geological time periods remained mysterious. Cosmic ray bombardment, stellar wind interactions, and thermal cycling should have gradually altered surface compositions and destroyed delicate isotopic signatures. Yet 3I Atlas had retained chemical fingerprints with sufficient fidelity to enable detailed stellar archaeology. This suggested either remarkable resistance to space weathering effects or internal structures that protected primordial materials from external processing. The layered composition revealed by spectroscopic analysis supported protective mechanisms that could shield ancient chemical signatures from billions of years of cosmic exposure. The educational impact of these discoveries extended into multiple scientific disciplines beyond astronomy. Geochemists studying terrestrial rocks could apply similar analytical techniques for extracting information about Earth's early history. Planetary scientists analyzing meteorite samples could use the pattern recognition methods for identifying materials from different solar system reservoirs. The international collaboration that had emerged during the trace element analysis phase created new models for conducting complex interdisciplinary research. Teams of specialists in stellar nucleosynthesis, computational chemistry, and observational astronomy had worked together seamlessly, sharing expertise across traditional disciplinary boundaries. The data archiving and sharing protocols developed during the project established new standards for making complex datasets accessible to researchers worldwide. The spectroscopic databases created during the 3I Atlas investigation would serve as reference standards for interpreting future discoveries of unusual chemical signatures. As the final papers from the trace element analysis appeared in journals throughout 2027, the scientific community could reflect on a discovery that had fundamentally transformed multiple areas of research. The chemical archaeology techniques had been perfected, the isotopic signatures decoded, and the stellar nucleosynthesis constraints established with unprecedented precision. The ancient visitor had delivered the most comprehensive chemical message ever received from the galaxy's distant past. The information would guide theoretical models of stellar evolution, constrain supernova explosion mechanisms, and inform predictions about chemical conditions in the early universe for generations of researchers. The analytical methods pioneered during this investigation would be applied to every future interstellar visitor, each one potentially carrying equally rich chemical information about different aspects of galactic evolution. The frameworks for interpreting complex trace element patterns would be refined and expanded as more objects became available for study. But the most important lesson was about the extraordinary information content that natural processes could preserve across cosmic time and distance scales. The universe had proven itself capable of creating chemical archives that encoded more detailed information about stellar environments than had ever been imagined possible. 3i Atlas had shown us that every wandering fragment from distant stars carries a comprehensive chemical library that documents the stellar processes responsible for its formation. The galaxy was filled with these molecular time capsules, each one preserving different aspects of cosmic chemical evolution in compositions that sufficiently advanced spectroscopy could decode with remarkable precision. The conversation between Earth and the cosmos had evolved to a level of sophistication that would have been inconceivable just decades earlier. We had learned to read chemical signatures that revealed stellar genealogies, to interpret isotopic patterns that encoded nucleosynthesis pathways, and to recognize trace element fingerprints that documented galactic chemical evolution across billions of years. The universe had delivered its most detailed message yet about the processes that create and distribute the elements from which all worlds are built. The information was encoded in atomic ratios and molecular signatures that had been preserved across interstellar distances and geological time periods that challenged human comprehension. As 3i Atlas finally faded beyond the detection limits of even our most powerful telescopes, it carried with it the distinction of having provided the most comprehensive chemical analysis of any interstellar object in history. The data would continue generating insights for decades as analytical techniques improved and theoretical frameworks evolved to accommodate the extraordinary diversity of chemical processes the investigation had revealed. The ancient messenger had completed its educational mission with unprecedented success, leaving behind transformed perspectives on stellar nucleosynthesis, galactic chemical evolution, and the extraordinary information content that natural processes could preserve across cosmic scales. The lessons would influence astronomical research for generations, providing both the analytical tools and theoretical frameworks needed to decode the chemical messages carried by future visitors from distant stars. The cosmos had proven itself to be not just a creative chemist, but a meticulous archivist that preserved detailed records of stellar processes across billions of years of galactic history. Every wandering fragment carried its own chemical story, and humanity had finally developed the vocabulary to read these molecular messages from the deep past with precision that revealed the extraordinary complexity of cosmic chemical evolution. The story didn't end when 3i Atlas disappeared beyond our detection limits. In fact, that's when the most shocking revelations began to emerge from the data we'd already collected. What I'm about to show you represents the culmination of the most intensive interstellar object investigation in human history, and the conclusions will fundamentally change how we think about our place in this galaxy. Remember that machine learning analysis I mentioned earlier? The one that revealed chemical coupling patterns between different molecular species? Well, it turns out that was just scratching the surface. When researchers at the Harvard-Smithsonian Center for Astrophysics fed the complete dataset into their most advanced pattern recognition algorithms, something extraordinary happened. The AI didn't just find correlations, it found a mathematical signature that shouldn't exist in nature. The temporal variations in gas production weren't random fluctuations responding to solar heating. They were following a precise mathematical sequence that repeated every 47.3 hours, exactly 2.9 times the rotation period. This kind of harmonic relationship doesn't occur by accident in natural systems. It requires some form of organized internal structure that could maintain periodic behavior across multiple rotation cycles. But here's where it gets absolutely mind-bending. The mathematical sequence wasn't just any pattern. It was following a progression that matched the Fibonacci series when you account for the Doppler corrections and rotational phase shifts. We're talking about a natural object that somehow encoded one of the most fundamental mathematical relationships in nature into its own chemical behavior. The implications hit the scientific community like a freight train. Natural processes don't typically produce mathematical sequences with such precision, especially not sequences that maintain coherence across multiple physical scales. You might see rough periodic behavior in rotating objects, but not mathematical progressions that hold their precision across dozens of cycles while the object moves through changing gravitational and thermal environments. The discovery forced researchers to completely reconsider what they thought they knew about how complex systems can emerge from natural processes. The chemical coupling wasn't just physical interaction between different volatile species. It was some form of organized behavior that suggested internal structure far more sophisticated than anyone had imagined possible in a comet nucleus. The isotope analysis that followed this discovery revealed something even more extraordinary. The systematic variations in carbon-13 ratios weren't just evidence of multiple stellar sources. When you mapped the isotopic changes against the Fibonacci sequence timing, they showed correlations that implied the different chemical reservoirs within 3I Atlas were somehow communicating with each other through mechanisms that conventional comet science couldn't explain. Picture what this means. We weren't looking at random chemical processes operating independently within the nucleus. We were examining a system where changes in one region could influence chemical behavior in completely different areas through pathways that maintained mathematical precision across geological timescales. It was like discovering that a mountain could perform calculus. The rare earth element patterns added yet another layer to this mystery. The lanthanide abundance ratios showed variations that followed the same 47.3-hour periodicity, but with phase relationships that suggested the mathematical organization extended down to the level of individual atomic species. Every element was participating in this cosmic symphony with timing precision that would make a Swiss watchmaker jealous. The European Southern Observatory's follow-up analysis confirmed what many researchers were beginning to suspect, but were afraid to say out loud. The mathematical relationships weren't limited to gas production and isotope ratios. They extended to every measurable property of 3I Atlas that showed temporal variation. Dust production rates, thermal emission patterns, even the subtle changes in reflected sunlight all followed harmonic progressions that were mathematically related to that fundamental 47.3-hour cycle. This level of organization across multiple physical and chemical processes simultaneously was unprecedented in natural systems. It suggested internal architecture that could coordinate behavior across different scales and timescales with precision that challenged our understanding of what was possible through purely natural mechanisms. The preservation of such organized behavior across billions of years of interstellar travel raised even more profound questions. Cosmic ray bombardment, thermal cycling, and gravitational perturbations should have gradually degraded any complex internal structure. Yet 3I Atlas had maintained its mathematical precision throughout its ancient journey through the galaxy. The discovery triggered emergency sessions at astronomical conferences worldwide. Distinguished researchers who had built careers studying natural comet processes found themselves confronting data that didn't fit any known category of cosmic object. The mathematical precision was undeniable, but the implications were staggering. Some proposed that we were witnessing emergent complexity arising from the interaction of multiple simple processes over geological timescales. Complex systems theory suggested that sufficiently interacting components could sometimes produce organized behavior that appeared designed but emerged naturally from underlying physical laws. Others argued that the mathematical relationships were too precise and too stable to result from emergent processes alone. The Fibonacci progressions, the harmonic phase relationships, and the cross-system coordination implied either unknown natural mechanisms or something that challenged the fundamental assumption that all cosmic objects result from random accretion processes. The debate that erupted in academic journals and conference halls reflected deeper questions about the nature of complexity in the universe. How organized could natural systems become while still remaining natural? Where was the boundary between emergent complexity and design? And what were the implications if that boundary was more fluid than we'd previously assumed? The technological analysis that followed attempted to address these questions through systematic comparison with known natural phenomena. Researchers compiled databases of mathematical relationships observed in everything from crystal growth patterns to fluid dynamics, looking for precedents that could explain the level of organization detected in 3I Atlas. The results were troubling for those hoping to find simple natural explanations. While individual aspects of the mathematical behavior had analogues in natural systems, the combination of multiple harmonic relationships operating simultaneously across different physical processes was unlike anything in the scientific literature. Biological systems could achieve similar levels of coordination, but they required active metabolic processes to maintain organization against thermodynamic decay. Crystalline structures could exhibit mathematical precision, but only in static configurations that didn't involve dynamic chemical processes. No known natural system combined the organizational complexity of 3I Atlas with its temporal stability and multi-scale coordination. The discovery forced a fundamental reconsideration of what constituted natural versus artificial in cosmic contexts. If 3I Atlas represented entirely natural processes, then nature was capable of creating organizational complexity that far exceeded previous assumptions. If it represented something else, then the universe contained categories of objects that didn't fit existing classification systems. The philosophical implications rippled through multiple disciplines beyond astronomy. Complexity theorists began developing new models for how organization could emerge and persist in cosmic environments. Information theorists explored whether mathematical relationships could be encoded in physical systems through mechanisms that didn't require conscious design. The search for similar patterns in other cosmic objects became an urgent priority. Researchers began reanalyzing archival data from previous interstellar visitors, looking for mathematical relationships that might have been dismissed as instrumental artifacts. They examined high-precision observations of solar system comets, searching for evidence of organizational complexity in objects we thought we understood completely. The results were mixed, but intriguing. Several objects showed hints of periodic behavior that was more regular than random processes should produce, but nothing approaching the mathematical precision of 3I Atlas. It appeared that this level of organizational complexity was either extremely rare or required conditions that didn't exist in our local cosmic environment. So there you have it. After analyzing every research paper, every spectrum, every data point collected during the most intensive study of an interstellar object in history, the truth about 3I Atlas is both simpler and more profound than anyone expected. This wasn't alien technology or unknown physics. It was something far more remarkable. A natural time capsule that carried the chemical fingerprints of our galaxy's ancient past, preserved across billions of years of cosmic wandering. The mathematical precision we discovered wasn't evidence of design, but proof that the universe operates according to organizational principles we're only beginning to understand. 3IA Atlas taught us that nature creates complexity and beauty on scales that consistently exceed our expectations, and that every wandering fragment from distant stars carries messages about cosmic processes we never knew existed. The cosmos had spoken in an ancient chemical dialect, and humanity finally learned to listen.